Hello and welcome to Infinite Science. Right now, beneath your feet, the ground is moving, not just trembling, but traveling. Continents drift like ships on an ocean of molten rock. Mountains breathe. Forests communicate through underground networks that stretch for miles. And deep in the ocean, creatures glow with their own light, painting the darkness in colors we're only beginning to understand. Earth is not a static rock orbiting a star. It is a living system, ancient, resilient, and stranger than most of us will ever realize. Today, we're going to explore 100 facts about our planet that feel almost unreal. Some will challenge what you thought you knew. Others will reveal connections so subtle they've been hidden in plain sight for millennia. We'll journey from the planet's molten core to the edge of space, from microscopic life that shouldn't exist to geological forces that reshape continents, from glowing oceans to singing whales, from immortal creatures to rocks that remember. This is not just a list of curiosities. This is a portrait of Earth as it truly is, a world far more complex, far more alive, and far more interconnected than the simple blue marble we see from space. Each fact we explore opens a window into deeper mysteries. Each revelation connects to others, forming a web of understanding about how our planet works, how it came to be, and why it remains the only place in the universe we know for certain harbors life. So, settle in, breathe, and let's journey together through the strangest truths about the only home we've ever known. Let's begin with the ground itself. The surface you're standing on is moving right now. Tectonic plates shift between 2 and 10 centimeters every year, about the same rate your fingernails grow. This might seem insignificantly slow, but over millions of years, this patient movement has assembled and broken apart supercontinents multiple times. Pangaea, the last supercontinent, existed just 200 million years ago when dinosaurs first appeared. Before that came Rodinia, assembled a billion years ago. And before that, others whose names are lost to deep time. Nuna, Kenorland, perhaps others we haven't yet discovered evidence of. Each supercontinent formed over hundreds of millions of years, existed for perhaps 100 million years, then fragmented. The cycle repeats endlessly, driven by convection currents in Earth's mantle. Earth's magnetic field isn't fixed, it flips. North becomes south, south becomes north. This has happened hundreds of times in our planet's history, at least 183 times in the last 83 million years alone. The last reversal occurred 780,000 years ago, and scientists believe we may be overdue for the next one. When these magnetic reversals happen, the field weakens dramatically, sometimes to just 10% of its normal strength. For brief periods in geological time, Earth's protective shield against cosmic radiation becomes fragile. Some researchers theorize these moments accelerated evolutionary leaps by increasing mutation rates. The evidence is circumstantial but intriguing. Certain evolutionary transitions and extinction events seem to coincide with periods of magnetic instability and increased cosmic ray exposure. Mountains are not permanent fixtures of the landscape. The Himalayas, the youngest and tallest mountain range on Earth, are still growing, rising about 5 millimeters each year as the Indian plate collides with the Eurasian plate at a rate of about 5 centimeters per year. Mount Everest is measurably taller today than when Sir Edmund Hillary first climbed it in 1953. But mountains also breathe. Seasonal changes cause them to expand and contract. During summer, the Matterhorn can grow by several centimeters as the rock heats and expands. In winter, it shrinks back. This breathing isn't metaphorical. Precise GPS measurements and satellite interferometry confirm that mountains swell and contract with the seasons, responding to temperature changes like living things. They also expand and contract daily with the sun's heating and cooling cycle, though by smaller amounts. Earth hums. The entire planet vibrates at extremely low frequencies, between 2 and 7 millihertz, far below human hearing. These vibrations, called free oscillations or Earth's hum, occur constantly, even when there are no earthquakes. Scientists still debate their exact cause. Some attribute them to ocean waves colliding with the seafloor, creating pressure waves that reverberate through the entire planet, like a bell being continuously struck. Others suggest atmospheric pressure changes, interactions between ocean waves and seafloor topography, or deep subsurface processes we don't yet understand. The hum is too low for human ears to detect. You'd need to slow it down about 1,000 times to hear it, but seismometers around the world record it continuously. It's as if the Earth is singing in notes so deep, only instruments can hear it. Studying this hum helps scientists understand Earth's interior structure in the same way doctors use ultrasound to see inside the human body. Beneath the continents lies a hidden ocean. Not liquid water, but water molecules trapped within minerals in the mantle. This reservoir, located in a layer called the transition zone, between 400 and 600 kilometers deep, may contain more water than all the surface oceans combined, perhaps 3 times as much. The mineral ringwoodite, stable only at the extreme pressures found in the transition zone, can hold water within its crystal structure, up to 2.5% of its weight. If this deep reservoir were suddenly released, it could fundamentally reshape our planet's surface, flooding continents and altering the global water cycle. Some scientists believe this hidden ocean plays a crucial role in plate tectonics, lubricating the descent of subducting plates and regulating the long-term water cycle over geological time. The existence of this water was confirmed in 2014 when scientists found a diamond that had formed in the transition zone and contained ringwoodite with water trapped inside, a piece of the deep Earth brought to the surface. Earth's core is as hot as the surface of the Sun, approximately 5,400 degrees Celsius at the boundary between the inner and outer core. Yet the inner core remains solid due to immense pressure, about 3.6 million atmospheres. The inner core is a massive iron-nickel crystal, roughly the size of the Moon, and about 1,200 kilometers in diameter, spinning within an outer core of liquid iron. And it rotates at a different speed than the rest of the planet, sometimes faster, sometimes slower than Earth's surface. Recent studies from 2023 suggest it may have stopped its differential rotation and even reversed direction, though the implications remain unclear and controversial. This differential rotation generates Earth's magnetic field through a process called the geodynamo. As liquid iron moves in the outer core, it creates electric currents, which produce magnetic fields. Without this geodynamo, we'd have no protection from solar radiation, no auroras. Compasses wouldn't work, and Earth might become as lifeless as Mars. Earth's gravity is not uniform across the surface. There are places where you weigh slightly more or less depending on the density of rock beneath you, the distance to the center of the planet, elevation, and the topography around you. Scientists map these variations using satellites, particularly the GRACE, Gravity Recovery and Climate Experiment satellites, to understand what lies hidden underground. These gravity maps have revealed ancient impact craters buried beneath kilometers of sediment, hidden mountain ranges under Antarctic ice sheets, and even helped locate mineral deposits and oil reserves. The gravity field is constantly changing as ice sheets melt, groundwater depletes, tectonic plates shift, and even as large earthquakes redistribute mass within Earth's crust. Your weight at the top of a mountain isn't just less because you're farther from Earth's center. It's also affected by the mass of the mountain itself, pulling you upward slightly. The Pacific Ocean is shrinking. Every year it gets about 2 to 3 centimeters smaller as the Atlantic Ocean expands at roughly the same rate. This is happening because new seafloor is being created at the Mid-Atlantic Ridge, a massive underwater mountain range where tectonic plates are pulling apart, while old seafloor is being consumed in subduction zones around the Pacific Ring of Fire, where oceanic plates dive beneath continental plates. In roughly 200 to 250 million years, the Pacific may close entirely, and the continents will collide again, forming a new supercontinent. Scientists have already named potential configurations: Pangaea Proxima, where the Americas collide with Antarctica and then Africa, or Amasia, where the Americas and Asia merge around the North Pole, or Eureka, where a new ocean forms down the Atlantic as the Pacific closes. Australia is already migrating north toward Asia at about 7 centimeters per year. The Americas are drifting west. Africa is splitting along the East African Rift, which may eventually become a new ocean. The future geography of Earth is being written in the slow motion of plates, and we can predict with reasonable confidence what the world will look like millions of years from now. Antarctica was once a tropical paradise, hard as that is to imagine when looking at its ice sheets today. 50 million years ago, during the Eocene epoch, it was covered in rainforests, with temperatures averaging around 20 degrees Celsius, warmer than present-day Paris. Fossils of palm trees and crocodile-like creatures have been discovered beneath the ice. Rivers flowed through lush forests. Insects buzzed. Dinosaurs had only recently gone extinct, and mammals were diversifying rapidly. The continent only began freezing about 34 million years ago when ocean currents shifted and isolated it at the South Pole. The Drake Passage opened between Antarctica and South America around 41 million years ago, allowing the Antarctic Circumpolar Current to form, a massive current that circles the continent like a cold moat, isolating it thermally and causing the ice sheets to grow. Now, Antarctica holds 70%. The Sahara Desert was green just 6,000 years ago, recent enough that we have archaeological evidence of the transformation. Ancient rock art depicts hippos, giraffes, elephants, crocodiles, and rivers. Archaeological evidence shows human settlements flourished there, fishing in permanent lakes and herding cattle beside rivers that no longer exist. Periodic shifts in Earth's axial tilt cause the Sahara to oscillate between desert and savanna roughly every 20,000 years. This transformation is called the African Humid Period, and it has repeated many times throughout Earth's history, perhaps hundreds of times. When Earth's tilt increases, summer sunlight intensifies over North Africa, strengthening monsoons and bringing rain. Vegetation spreads, creating a feedback loop where plants increase humidity and precipitation. When the tilt decreases, the monsoons weaken, vegetation dies, the desert returns, and the feedback reverses. We're currently in a dry phase, but in another 15,000 years, the Sahara may bloom again. The transition between green Sahara and desert can happen surprisingly quickly, perhaps within just a few centuries, as feedback loops amplify small changes in precipitation. Earth's atmosphere extends far beyond where you think it ends. The outermost layer, the exosphere, reaches halfway to the moon, roughly 190,000 kilometers into space. At these altitudes, particles are so sparse that they rarely collide. An atom might travel hundreds of kilometers without encountering another atom. The boundary between Earth's atmosphere and space is arbitrary. There's no sharp edge, just a gradual fading into emptiness. The Kármán line at 100 kilometers altitude is often used as the boundary of space, but it's just a convenient definition. Technically, the moon orbits within Earth's atmosphere. Though at that distance, the atmosphere is barely distinguishable from the vacuum of space, so tenuous that it contains only a few atoms per cubic centimeter. Our planet loses about 90 tons of atmosphere to space every day, roughly 3 kilograms per second. Lightweight molecules like hydrogen and helium escape Earth's gravity and drift into the void through a process called atmospheric escape. Over billions of years, this slow leak has dramatically reshaped our atmosphere. Early Earth had much more hydrogen, perhaps similar to the gas giants in composition. As hydrogen escaped, the chemical balance shifted, allowing oxygen produced by photosynthesis to accumulate rather than reacting away with hydrogen. This oxygen accumulation enabled complex life to evolve. Mars lost most of its atmosphere this way. Without a magnetic field to protect it from the solar wind, Mars's atmosphere was stripped away over billions of years, transforming it from a potentially habitable world with liquid water and a thick atmosphere into the cold, dry desert we see today. Earth is lucky. Our magnetic field has prevented the same fate, though we still lose atmosphere continuously. Earth once had rings, like Saturn, one of the most surprising recent discoveries in planetary science. Around 466 million years ago, during the Ordovician period, an asteroid broke apart near our planet after passing within Earth's Roche limit, and the debris formed a temporary ring system that may have lasted several million years. Evidence comes from an unusual concentration of impact craters, all located near the equator from that time period, suggesting debris fell preferentially along the equator plane, exactly what you'd expect from a ring system as material gradually spiraled down. During this time, life in the oceans would have looked up through the water and seen a band of light crossing the sky from horizon to horizon. The rings eventually rained down as meteorites, leaving their mark in the geological record. Some scientists speculate the rings may have caused climate cooling by shading Earth's surface, contributing to an ice age that occurred during the same period. The moon is moving away from us in a process that will continue for billions of years. Every year, it drifts about 3.8 centimeters farther due to tidal interactions, a phenomenon precisely measured by reflecting laser beams off mirrors left on the lunar surface by Apollo astronauts. Earth's rotation creates tidal bulges in the oceans, not just on the side facing the moon, but also on the opposite side. These bulges are pulled forward by Earth's rotation, creating a slight gravitational pull on the moon ahead of it in its orbit. This gravity tugs on the moon, gradually accelerating it, which causes its orbit to expand and its orbital period to lengthen. Billions of years ago, the moon was so close that Earth's day was only about 5 hours long. Tides were massive, hundreds of meters high, reshaping coastlines twice per day. Early Earth would have been a dramatically different place, with the moon looming enormous in the sky, perhaps 10 times larger in apparent size than today, creating extreme tides that may have played a role in the origin of life by concentrating organic molecules in tidal pools and creating cycling wet-dry conditions that could have driven chemical evolution. Earth's rotation is slowing due to tidal friction with the moon. Days are getting longer, by about 1.7 milliseconds per century. This might seem insignificant, but over geological time, the effect is substantial. In the age of the dinosaurs, 100 million years ago, a day was closer to 23 hours. 620 million years ago, a day was only 21.9 hours long. We know this from growth rings in ancient corals and shells, which record daily and seasonal cycles like tree rings. Just as tree rings show annual growth with variations based on climate, coral skeletons show daily growth bands and seasonal patterns. By counting these daily bands between seasonal markers, paleontologists can determine how many days were in a year at different points in Earth's history. As Earth spins slower, the moon moves farther away. The two processes are linked through the conservation of angular momentum. As Earth loses rotational energy through tidal friction, the moon gains orbital energy. Eventually, in about 50 billion years, if the sun doesn't engulf both bodies first, Earth and moon would become tidally locked, with the same side of Earth always facing the moon, and a day would equal about 47 current days. But the sun will become a red giant and destroy both Earth and moon long before this happens. Lightning strikes Earth about 100 times per second, roughly 8.6 million times per day, or about 3 billion times per year. Each bolt can reach temperatures of 30,000 degrees Celsius, 5 times hotter than the surface of the sun. Lightning creates shock waves we hear as thunder, but it also produces rare phenomena like ball lightning, sprites, and elves. Ball lightning appears as glowing spheres that float through the air, sometimes passing through windows or walls before vanishing. Despite thousands of reports over centuries, scientists have struggled to reproduce it in laboratories, and its physical mechanism remains mysterious. Sprites are massive electrical discharges that occur above thunderstorms, reaching up to 90 kilometers into the mesosphere. They were only discovered in 1989 and appear as brief red flashes. Elves are expanding rings of light in the ionosphere caused by electromagnetic pulses from lightning. Some lightning strikes upward from the ground towards space. Called gigantic jets, these rare bolts shoot from the tops of thunderstorms into the ionosphere, reaching altitudes of 80 to 90 kilometers and transferring enormous amounts of electric charge from the atmosphere to space. They were only discovered in 2002 because they're difficult to observe, lasting only a fraction of a second, occurring primarily over oceans or remote areas, and requiring observers to be looking at exactly the right place at the right time. Pilots occasionally report seeing them, describing brilliant blue or purple columns erupting from thunderheads toward space. These jets may play a role in connecting Earth's electrical circuit, transferring charge between the surface and the ionosphere, and completing the circuit that maintains Earth's electric field. Volcanic eruptions can change the weather worldwide through the injection of aerosols into the stratosphere. The 1815 eruption of Mount Tambora in Indonesia ejected so much ash and sulfur dioxide into the atmosphere that it caused the year without a summer in 1816. Crops failed across Europe and North America. Snow fell in June in New England. Frost occurred every month of the year in parts of the northern United States. People starved. The ash, and especially sulfur dioxide, which forms reflective sulfate aerosols, reflected sunlight back into space, cooling the planet by about 0.5 degrees Celsius for several years. The eruption killed tens of thousands directly through the blast and pyroclastic flows, but the climate effects killed hundreds of thousands more through famine and disease. It was the most deadly volcanic eruption in recorded history. But even larger eruptions have occurred in the geological past. The Toba supereruption 74,000 years ago may have cooled the planet by several degrees and created a volcanic winter lasting years, potentially creating a genetic bottleneck in human evolution as populations crashed. Earth has a second layer of mountains invisible from the surface, underwater. The mid-ocean ridges form the longest mountain chain on the planet, stretching over 65,000 kilometers, more than 1.5 times Earth's circumference. These underwater mountains mark the boundaries where tectonic plates pull apart, and new seafloor is born from rising magma at a rate of several centimeters per year. The ridges are volcanically active, with eruptions occurring constantly along their length, though most go unobserved beneath kilometers of water. At the ridge crests, the seafloor is young, sometimes only a few thousand years old, still hot and fresh from volcanic activity. As you move away from the ridge, the seafloor gets progressively older, cooler, and deeper as the lithosphere cools and contracts. This creates a symmetrical pattern of magnetic stripes on either side of the ridge, recorded as the seafloor forms during periods when Earth's magnetic field has different orientations. This pattern was crucial evidence that helped confirm the theory of plate tectonics in the 1960s. Some rocks float on water. Pumice, formed from volcanic lava filled with gas bubbles, is less dense than water because it contains so many air pockets that it's more air than rock. After eruptions, vast rafts of pumice can float across oceans for years, sometimes covering areas the size of cities, transporting marine organisms to new habitats thousands of kilometers away and playing a surprising role in dispersing life across ocean basins. A single eruption can create pumice rafts large enough to be hazards to shipping. Boats can become stuck in fields of floating rock. Satellites have tracked rafts the size of Belgium drifting across the Pacific after submarine volcanic eruptions. Eventually, the pumice becomes waterlogged as pores fill with water, and it sinks, but not before carrying barnacles, algae, corals, and other organisms vast distances from their origin, potentially introducing species to new ecosystems. The oldest rocks on Earth are over 4 billion years old, though finding such ancient samples is extraordinarily rare. The Akastic gneiss in northwestern Canada dates to 4.03 billion years, formed when Earth was still being bombarded by asteroids. The moon was much closer, days were much shorter, and the atmosphere lacked oxygen. These ancient rocks are incredibly rare because most early crust has been destroyed by erosion, weathering, and the constant recycling of plate tectonics. Continental crust is repeatedly modified, melted, and reformed. They provide our only direct window into Earth's infancy, a time when the planet was hot, volcanic, and covered by a global ocean. The rocks tell us that continental crust existed much earlier than previously thought, and that Earth cooled rapidly after formation. Finding even older rocks is a major goal of geology, as they could tell us about the conditions that allowed life to emerge and whether the late heavy bombardment, a period of intense asteroid impacts around 3.9 billion years ago, actually occurred or is an artifact of lunar geology. Earth's oldest mineral grains are even older than the oldest rocks, providing glimpses of Earth's earliest history. Zircon crystals found in Jack Hills, Australia, date to 4.4 billion years, only 160 million years after the planet formed, and just after the moon forming impact. These tiny crystals, often smaller than a grain of sand, survived the destruction of their parent rocks through billions of years of erosion and were incorporated into younger formations. Chemical analysis of the zircons, particularly oxygen isotope ratios, suggest they formed in the presence of liquid water, meaning Earth may have had oceans much earlier than previously thought, possibly within 200 million years of formation. If true, this extends the window for life's origin considerably. It suggests Earth became habitable very quickly after formation, perhaps even before the late heavy bombardment, raising the possibility that life originated multiple times as early oceans were repeatedly evaporated by impacts, only to reform and potentially seed life again. Now let's descend into the oceans, Earth's most alien environment, covering 71% of the surface, yet remaining largely unexplored. The ocean glows at night in certain conditions. Bioluminescent organisms create waves of blue-green light along coastlines in a phenomenon called milky seas or mareal. Dinoflagellates, tiny plankton measuring just millimeters across, emit light when disturbed by a chemical reaction involving luciferin and luciferase. On certain nights, particularly in warm tropical waters, during blooms of these organisms, entire beaches shimmer as if the stars have fallen into the water. Walk through the shallows and every footstep glows. Swim through the water and your body leaves a trail of light. Kayak through bioluminescent bays like Mosquito Bay in Puerto Rico, and your paddle leaves trails of sparkling light. This light serves as a defense mechanism. The sudden flash can startle predators or attract even larger predators to consume whatever disturbed the plankton. It's one of nature's most magical displays, experienced by relatively few people, but unforgettable to those who witness it. The deepest part of the ocean, the Challenger Deep in the Mariana Trench, reaches 10,994 meters below the surface, nearly 11 kilometers down. If you placed Mount Everest, the tallest mountain at 8,849 meters, at the bottom of the Challenger Deep, its peak would still be over 2 kilometers underwater. At the bottom of the Mariana Trench, the pressure is over 1,000 times greater than at sea level, approximately 1,086 bar or 15,750 pounds per square inch, equivalent to 50 jumbo jets stacked on top of you, or about 3 SUVs balanced on your thumbnail. Yet life thrives there in conditions that would instantly crush most organisms. Strange fish with translucent skin and soft bones, amphipods the size of dinner plates, sea cucumbers, and microbes that feed on chemicals seeping from the seafloor have all been found. The deepest fish ever filmed was a snailfish at 8,178 meters in the Izu Ogasawara Trench, living in near-total darkness under crushing pressure, feeding on tiny crustaceans. These deep-sea organisms have specialized proteins that remain functional under extreme pressure and cells filled with osmolytes that prevent compression. There are underwater waterfalls beneath the ocean surface, invisible from above. The Denmark Strait Cataract, between Iceland and Greenland, is the largest waterfall on Earth by volume. Cold, dense water from the Nordic Seas plunges 3.5 kilometers down the continental slope into the Erminger Sea, carrying an astounding 175 million cubic feet of water per second, equivalent to 2,000 Niagara Falls, or about 25 times the flow of all rivers on Earth combined. You can't see it from the surface because it occurs beneath the ocean, but beneath the waves, this massive flow continuously cascades down.
The falling water is so cold and dense, chilled by contact with Arctic ice, and made extra dense by high salinity, that it sinks beneath warmer water, creating an underwater river that flows along the ocean floor for thousands of kilometers. This thermohaline circulation is crucial for global climate, distributing heat and nutrients throughout the world's oceans.
The ocean has rivers within it, not just local currents, but vast conveyor belts of moving water. The Gulf Stream, a massive warm current in the Atlantic, moves 30 times more water than all the world's rivers combined, about 100 million cubic meters per second at its peak. It regulates climate across entire continents. Without the Gulf Stream, Western Europe would be significantly colder. London would have a climate more like Labrador, Canada, at similar latitude. The current system functions like a planetary conveyor belt, part of the Atlantic meridional overturning circulation, redistributing heat from the equator toward the poles. Benjamin Franklin created the first map of the Gulf Stream in 1769, after noticing that mail ships took different amounts of time crossing the Atlantic depending on their route. He consulted with his cousin, a whaling ship captain, who knew the current well, and realized that ships sailing with the current traveled much faster. The Gulf Stream is up to 100 kilometers wide, up to 1.5 kilometers deep, and flows at speeds up to 2.5 meters per second, faster than most rivers. There are lakes under the ocean, not puddles, but actual distinct bodies of water on the seafloor. These brine pools are so salty and dense that they form separate bodies of water resting on the ocean floor. They have distinct shorelines, waves created by underwater currents, and even their own ecosystems. The water in these pools can be 3 to 8 times saltier than normal seawater, and often contains high concentrations of methane, hydrogen sulfide, and other dissolved chemicals. Creatures that swim into them often die instantly from the toxic combination of extreme salinity and poisonous gases. Their bodies can be seen accumulated along the shores of these underwater lakes, creating eerie graveyards. But some specialized organisms thrive at the edges, mussels and tube worms that host bacteria capable of surviving the extreme conditions. These brine pools form when ancient salt deposits buried beneath the seafloor dissolve, and the super salty water seeps up through the sediment, pooling in depressions. They provide insight into how life might survive in extreme environments on other worlds, such as beneath the ice of Jupiter's moon, Europa. The ocean is full of sound, far from the silent world many imagine. Whales sing songs that can travel thousands of kilometers through the ocean, carried by the SOFAR channel, a layer where temperature and pressure conditions create a waveguide that channels sound waves horizontally with minimal loss. Before the noise of modern shipping, a blue whale's call could cross entire ocean basins. A whale near Antarctica could theoretically be heard off the coast of Alaska, thousands of kilometers away. Blue whales produce sounds at frequencies as low as 14 Hz, far below human hearing range, which starts around 20 Hz, and at volumes up to 188 decibels, among the loudest sounds produced by any animal. The songs are complex, with repeating patterns and variations that change over time. Humpback whales create songs that last up to 20 minutes and are repeated for hours during breeding season. Males sing these songs, and remarkably, all the males in a region sing the same song, which evolves gradually over time. All the whales modify their songs in unison in a slow cultural evolution, like a changing musical tradition passed down through generations. Some recordings from the Cold War-era hydrophone networks, originally designed to detect Soviet submarines, captured sounds we still can't fully explain. Mysterious low-frequency noises, biological or geological in origin, remain subjects of scientific investigation and speculation. The bloop, a mysterious ultra-low frequency sound detected in 1997 by the U.S. National Oceanic and Atmospheric Administration, was one of the loudest underwater noises ever recorded, loud enough to be detected by sensors over 5,000 kilometers apart. Scientists now believe with reasonable confidence that it was the sound of an ice breaking and scraping along the seafloor as it calved from an Antarctic ice shelf. But for years, Its origin sparked speculation about unknown sea creatures, particularly giant squids or other undiscovered large marine animals. The hydrophone network, called SOSUS, was designed to track Soviet submarines during the Cold War, but ended up revealing how acoustically active the ocean is, constantly filled with sounds from whales, seismic activity, ships, ice movements, and mysterious sources we haven't yet identified. Coral reefs, though they cover less than 1% of the ocean floor, only about 280,000 square kilometers total, support around 25% of all marine species. They are living structures built by colonies of tiny animals over thousands of years. Each coral polyp, typically just millimeters across, secretes calcium carbonate, slowly constructing the reef framework. Some reefs have been growing more or less continuously for over 50 million years, building layer upon layer as sea levels rose and fell with ice ages, creating massive limestone structures. Coral reefs are among the most diverse ecosystems on Earth, rivaling rainforests in species richness. A single reef can host thousands of species, fish, invertebrates, algae, and microbes, all interconnected in complex relationships. The Great Barrier Reef alone supports over 1,500 fish species, 400 coral species, 4,000 mollusk species, and countless other organisms. Coral spawning is one of nature's most spectacular synchronized events. It happens once a year on certain reefs, timed to the lunar cycle and water temperature. On a specific night, determined primarily by the full moon in spring or summer and water reaching a critical temperature, billions of coral polyps release eggs and sperm simultaneously across entire reef systems. The synchronization is remarkable. Sometimes within a 30-minute window, an entire reef releases gametes, creating underwater snowstorms of tiny pink and orange bundles floating upward through the water. This mass spawning event overwhelms predators through sheer numbers, ensuring that some offspring survive despite countless fish and invertebrates feeding on the eggs. Divers who witness coral spawning describe it as magical. The water suddenly fills with billions of tiny bundles, and visibility drops to almost nothing as the water becomes a soup of coral gametes. The timing must be precise for fertilization to occur, so corals coordinate using environmental cues, including lunar cycles, seasonal temperature changes, and perhaps chemical signals from other corals, though the exact mechanisms remain partially mysterious. The Great Barrier Reef is visible from space and shows up in satellite imagery as a massive structure stretching along Australia's northeast coast. It extends over 2,300 kilometers and covers an area of approximately 344,400 square kilometers, making it the largest structure ever made by living organisms. It's so large that it's sometimes claimed to be visible to the naked eye from the moon, though this is likely an exaggeration. Astronauts report that from low Earth orbit, the reef is visible as a lighter blue-green area against the darker ocean, but from the moon, no human-made or biological structures are individually visible. But reefs are not permanent. Many modern reefs are built on a remains of older reefs that died during past climate shifts, particularly during ice ages when sea levels dropped and exposed reefs to air, killing them. Beneath the living surface lie layers of fossil coral, recording the ocean's history like tree rings, with alternating layers of growth and death corresponding to favorable and unfavorable periods. Core samples from reefs reveal centuries of environmental change, El Niño events, temperature fluctuations, periods of faster and slower growth responding to nutrient availability and water conditions. Sharks have been around longer than trees, which puts their evolutionary success in perspective. The first sharks appeared over 400 million years ago during the Silurian period. Trees evolved around 350 million years ago during the Devonian. Sharks have survived all 5 major mass extinctions that wiped out most other species, including the Permian extinction that killed 96% of all marine species, and the Cretaceous extinction that killed the dinosaurs. They've remained largely unchanged in basic body plan because it's remarkably successful, streamlined for hydrodynamic efficiency, with replaceable teeth that grow in conveyor belt fashion throughout their lives, keen senses including the ability to detect electrical fields from muscle contractions of prey, and adaptability to various environments, from shallow reefs to the deep ocean. Some shark species today look nearly identical to fossils from 150 million years ago. Sharks are often called living fossils, though they've actually undergone significant evolutionary changes. Modern sharks are quite different from ancient forms, but the basic body plan has proven so effective that it persists. Some sharks glow in the dark, adding to their alien qualities. Kite-fin sharks, discovered to be bioluminescent in 2021, are the largest known glowing vertebrates, reaching up to 1.8 meters in length. They use bioluminescence for counter-illumination camouflage. The light helps them hunt in the deep sea by making them invisible from below. When viewed from beneath, their glowing bellies match the faint light filtering down from the surface, erasing their silhouette against the sky. Many deep-sea creatures use this strategy. The bioluminescence may also help them communicate with other members of their species and potentially confuse prey or predators. The light is produced by photophores, specialized organs containing light-producing bacteria or chemical reactions involving luciferin and luciferase. Some sharks may also use bioluminescence to attract prey, with glowing lures similar to anglerfish. The ocean contains enough gold to make everyone on Earth rich, at least in theory. There are approximately 20 million tons of gold dissolved in seawater, which would be enough to give every person on Earth roughly 9 pounds of gold. But it's dissolved at concentrations so low, about 13 billionths of a gram per liter, or 13 parts per trillion, that extracting it is economically impossible with current technology. The energy cost of processing enough water to extract even a single gram of gold would far exceed the value of the gold obtained. The same is true for many other valuable metals. The ocean is a vast, dilute solution of nearly everything. Every element on the periodic table exists somewhere in seawater, washed there over billions of years by rivers eroding rocks and underwater volcanoes leaching minerals. Seawater is a complex chemical soup containing sodium, chloride, magnesium, sulfur, calcium, potassium, and trace amounts of literally every other element, including uranium, mercury, and even radioactive isotopes. There are more historical artifacts underwater than in all the museums on Earth combined, an underwater museum waiting to be explored. An estimated 3 million shipwrecks rest on the ocean floor, along with countless submerged cities, ancient harbors, crashed aircraft, and other remnants of human activity. These wrecks preserve snapshots of human history spanning thousands of years. Some wrecks are so well preserved in cold, deep water, far from oxygen and wood-eating organisms, that archaeologists can study construction techniques, trade routes, technologies, and cultures that left few records on land. The lack of oxygen in deep water prevents wood from rotting, and the cold inhibits organisms that would normally consume organic material. Ships that sank thousands of years ago can emerge looking remarkably intact, with organic materials, pottery, tools, and even food preserved. The Mediterranean sea floor contains wrecks spanning from ancient Phoenician vessels to Roman galleys to World War II warships, each one a time capsule. Sea level is not level. The ocean's surface is not flat, but undulates with variations as large as 2 meters from place to place. Ocean height varies depending on gravity, currents, temperature, salinity, and wind patterns. The Pacific Ocean, for instance, sits about 20 centimeters higher on average than the Atlantic due to differences in density, temperature, and the piling up of water by prevailing winds. This difference is maintained by wind patterns, the Earth's rotation, and the restriction of flow between oceans. If ocean currents suddenly stopped, water would redistribute dramatically according to gravity alone, flooding some coasts and exposing others. The shape of the ocean's surface actually reflects the topography of the seafloor beneath it. Gravity anomalies from underwater mountains and trenches create subtle bulges and depressions in the water surface. Satellites can measure these variations with precision of a few centimeters, allowing oceanographers to map seafloor features that have never been directly observed. In fact, we have better topographic maps of Mars and the Moon than of our own ocean floor. The ocean is getting louder, and this has consequences for marine life. Human activity, shipping, drilling, construction, military sonar, and seismic surveys for oil and gas has increased ocean noise levels dramatically, particularly at low frequencies that travel far underwater. Ambient noise levels in some parts of the ocean have doubled every decade since the 1960s. This disrupts marine life that relies on sound for navigation, communication, feeding, and reproduction. Whales must call louder or change their frequencies to be heard over the din of ship engines. Some populations have shown significant changes in vocal behavior. Beaked whales and other deep-diving species are particularly sensitive to sonar. Naval exercises using loud sonar have been definitively linked to mass strandings of beaked whales, likely by disrupting their diving behavior and causing decompression sickness. The noise pollution we've added to the ocean may have cascading consequences we're only beginning to understand, potentially affecting ecosystem function over vast areas. There are underwater volcanoes everywhere beneath the ocean. Far more volcanic activity underwater than on land. More than 75% of all volcanic activity on Earth occurs beneath the ocean, largely unseen by humans. The mid-ocean ridges form the longest mountain chain on the planet. Over 65,000 kilometers of underwater volcanic mountains wrapping around the globe like seams on a baseball. New seafloor is constantly being created at these spreading centers at rates of several centimeters per year, while old seafloor is consumed at subduction zones, where oceanic plates dive beneath continental plates. The ocean floor is, on average, much younger than the continents, constantly recycling itself through plate tectonics. The oldest oceanic crust is only about 200 million years old, found in the far western Pacific, while continental crust can be billions of years old. There are also countless isolated submarine volcanoes called seamounts. Estimates suggest there may be 100,000 seamounts taller than 1,000 meters, and perhaps millions of smaller ones, most of which have never been surveyed. Hydrothermal vents spew water superheated to over 400 degrees Celsius, sometimes reaching 464 degrees Celsius, hot enough to melt lead. The water doesn't boil despite these extreme temperatures because of the immense pressure at depth. At 2,500 meters, the pressure is about 250 atmospheres, emerges in dark plumes called black smokers, or lighter plumes called white smokers, depending on the minerals dissolved in the water. These vents support entire ecosystems that survive without sunlight, using chemical energy instead of solar energy as the base of the food web. Bacteria and archaea convert chemicals like hydrogen sulfide into usable energy through chemosynthesis. Entire food webs, including giant tube worms up to 2.4 meters long, blind white crabs, shrimp lacking eyes but with heat-sensing organs on their backs, and numerous other species found nowhere else, depend on these chemosynthetic bacteria. When hydrothermal vents were discovered in 1977 during an expedition to the Galapagos Rift, they revolutionized our understanding of where and how life can exist. Before this discovery, scientists assumed all life ultimately depended on photosynthesis and sunlight. The discovery of these vent ecosystems expanded the possibilities for life in the universe. If life can thrive near hydrothermal vents on Earth, perhaps it exists near similar vents on ocean worlds like Europa or Enceladus. Some organisms at hydrothermal vents live longer than anywhere else on Earth, despite, or perhaps because of, the seemingly harsh environment. Giant tube worms have been found that are over 250 years old based on growth rate measurements, growing less than a millimeter per year in the cold water surrounding the vents. In the stable environment of the deep sea, with abundant chemical energy and freedom from seasonal variations and most predators, life proceeds slowly but persistently. These worms have no mouth, gut, or anus. They survive entirely through symbiotic bacteria living in specialized organs called trophosomes that fill most of their body cavity. The worms absorb hydrogen sulfide, oxygen, and carbon dioxide through their red plumes and transport them to the bacteria, which use the chemical energy to produce organic compounds that feed the worm. It's one of the most remarkable symbiotic relationships known. The ocean absorbs about 25 to 30% of the carbon dioxide humans emit into the atmosphere through burning fossil fuels and deforestation. This has significantly slowed climate change. Without ocean uptake, atmospheric CO2 levels and temperatures would be much higher than they are. But this comes at a serious cost to ocean chemistry. As CO2 dissolves in seawater, it forms carbonic acid through a series of chemical reactions, making the ocean more acidic, lowering its pH. This process is called ocean acidification, sometimes called the other CO2 problem. Since the beginning of the Industrial Revolution, ocean pH has already dropped by about 0.1 units, which represents a 30% increase in acidity, because pH is a logarithmic scale. This may not sound like much, but it's occurring faster than at any time in at least the past 300 million years, and possibly much longer. Ocean acidification threatens shell-forming organisms like corals, mollusks, pteropods, and many species of plankton that build shells from calcium carbonate. In more acidic water, forming and maintaining calcium carbonate structures becomes more difficult and energy-intensive. If these foundational species collapse, particularly the plankton that form the base of many marine food webs, entire ecosystems could unravel, with devastating consequences for ocean life and the hundreds of millions of people who depend on ocean resources for food and livelihood. There are waves beneath the ocean surface, internal waves that are invisible from above but can be massive. Internal waves occur where water layers of different densities meet, typically between warm surface water and cold deep water, or between water masses of different salinities. These internal waves can be hundreds of meters tall as skyscrapers, and travel for hundreds of kilometers, moving water masses back and forth. They're typically much slower than surface waves, moving at speeds of several kilometers per hour rather than meters per second, but they involve enormous amounts of water and energy. These hitting waves play a crucial role in mixing nutrients between surface and deep waters and regulating ocean temperatures. They affect submarines, which can encounter unexpected currents when passing through internal waves. They can be detected from satellites by their subtle effects on surface roughness. Some of the largest internal waves occur in the South China Sea, generated by tidal flow over underwater ridges, creating waves that can be over 200 meters tall internally, despite causing barely visible ripples on the surface. The ocean floor is scarred by deep trenches, marking zones where tectonic plates collide, and one is forced beneath the other in a process called subduction. Deep trenches are the deepest parts of the ocean, reaching depths of 10 to 11 kilometers. The Mariana Trench is the most famous, but there are 27 other deep ocean trenches around the world, most of them around the Pacific Ring of Fire. These trenches are wounds in the Earth's crust, where the seafloor is being consumed and recycled into the mantle, completing the cycle of plate tectonics. At trenches, oceanic crust that formed at mid-ocean ridges millions of years ago, after traveling thousands of kilometers across the ocean floor, finally descends back into the Earth. As the plate descends, earthquakes are generated at the interface between plates, including some of the most powerful earthquakes on Earth, like the magnitude 9.1 Tohoku earthquake in Japan in 2011, and the magnitude 9.5 Valdivia earthquake in Chile in 1960, the most powerful earthquake ever recorded. Eventually, the descending rock will melt in the mantle, become part of magma chambers beneath volcanoes, rise as magma, erupt, and form new crust elsewhere, a complete cycle that takes hundreds of millions of years. In this way, rocks that once formed the ocean floor could eventually become part of a mountain range on a continent, carrying with them chemical signatures of their journey through the Earth's interior. Let's turn to life,
persistent, adaptable, and impossibly resilient beyond anything we might imagine possible. The immortal jellyfish can reverse its aging process, effectively achieving biological immortality. When injured, stressed, starved, or simply old, Turritopsis dohrnii reverts to its juvenile polyp stage and begins life again, potentially repeating this cycle indefinitely. It's the only known animal capable of completely reversing its life cycle to a sexually immature stage. Scientists study this jellyfish intensely, hoping to understand the mechanisms of aging and cellular regeneration.
The jellyfish doesn't simply heal or regenerate damaged parts. It undergoes cellular transdifferentiation, transforming its adult cells back into different cell types, reorganizing its body plan, and essentially starting over as a polyp that will eventually grow into an adult again. It's like a butterfly turning back into a caterpillar or a frog reverting to a tadpole. This ability challenges our fundamental understanding of the life cycle itself and raises questions about whether aging is truly inevitable or simply the way most organisms happen to work. Of course, the jellyfish isn't truly immortal. It can still be eaten, killed by disease, or destroyed by physical damage. But if conditions remain favorable, there's no apparent biological limit to how many times it can reset its life cycle. Tardigrades are nearly indestructible eight-legged microanimals that have survived Earth's 5 major mass extinctions. These microscopic animals, typically measuring 0.3 to 0.5 millimeters in length, can survive being frozen to near absolute zero at -273 degrees Celsius, heated to 150 degrees Celsius, exposed to radiation levels thousands of times higher than would kill humans instantly, pressures 6 times greater than the deepest ocean trenches, the vacuum of space, and years without food or water. They've been found everywhere on Earth, in the Himalayas at altitudes over 6,000 meters, in deep ocean trenches, in Antarctic ice, in hot springs, in sand dunes, and even in parking lot moss.
Tardigrades achieve these extremes by entering a state called cryptobiosis. They expel almost all water from their bodies, retaining only about 3% of normal hydration, replacing the water with a sugar called trehalose that protects cellular structures. They fold into a dormant structure called a tun that resembles a tiny barrel, retract their legs, and halt their metabolism completely. In this state, they can survive for decades. The record is a Japanese specimen revived after 30 years of cryptobiosis, though some researchers believe they could potentially survive even longer. When conditions improve, they rehydrate and resume normal life within hours, as if nothing happened.
In 2007, tardigrades became the first animals to survive prolonged exposure to space when they were sent outside the International Space Station. After 10 days exposed to cosmic radiation and the vacuum of space, many of them survived and even successfully reproduced afterward. Bacteria have been revived from 250-million-year-old salt crystals found in New Mexico, sealed away since the Permian period, before dinosaurs existed. These ancient microbes, isolated from the world for a duration longer than mammals have existed on Earth, resumed normal metabolic activity and reproduction when exposed to nutrients in the laboratory. This raises profound questions about how long life can remain dormant and whether similar organisms could survive in extreme environments on other planets or moons, or perhaps even survive the long journey between planets on meteorites, seeding life across the solar system through panspermia. Even more remarkably, bacteria have been found in 100-million-year-old ocean sediments beneath the seafloor, at depths of over 2,500 meters below the ocean floor. These bacteria appear to be alive, but have incredibly slow metabolism, potentially dividing only once every 1,000 years or longer. If life can sleep for hundreds of millions of years on Earth, perhaps it could survive similar timeframes in Martian rocks or in the subsurface oceans of icy moons, waiting for conditions to improve. Life exists miles beneath Earth's surface in a hidden biosphere we're only beginning to understand.
An entire ecosystem of bacteria and archaea lives in cracks within Earth's crust, in groundwater, in pores between rocks, and in petroleum deposits. Some scientists estimate that this deep subsurface life could represent more biomass than all surface life combined. Potentially 70% of all bacteria and archaea on Earth live underground. These organisms live incredibly slowly compared to surface life. Some subsurface bacteria divide only once every 1,000 years or even longer. One study estimated certain bacteria divide perhaps once every 10,000 years, raising questions about whether they should even be considered alive in the conventional sense or in some kind of extended suspended animation. They exist in near total darkness, feeding not on organic matter but on minerals and chemical reactions in the rock. They extract energy from reactions between rocks and water, from radioactive decay of elements like uranium and thorium, and from geological hydrogen produced by reactions between water and iron-containing minerals. It's a hidden world that most people never consider, an entire domain of life divorced from sunlight and the surface ecosystem. These deep organisms may represent some of the oldest continuously existing lineages on Earth, having lived in stable underground conditions potentially for billions of years, while surface life went through mass extinctions and dramatic evolutionary transformations. They may be our best analog for life on other worlds, where subsurface environments might be more hospitable than harsh surfaces. There are organisms living inside volcanoes and thriving in conditions that would sterilize most life. Thermophiles, heat-loving microbes, live in scalding acidic water near volcanic vents. One species, strain 121, can survive and reproduce at 121 degrees Celsius, the temperature used to sterilize medical equipment in autoclaves, hot enough to kill virtually every other known organism. These extremophiles have expanded the boundaries of where we expect to find life. They use proteins and membranes that remain stable at temperatures that would cause normal proteins to denature and cells to disintegrate. The proteins are more rigid, with additional chemical bonds that prevent them from unfolding. The membranes contain different lipids that remain intact at high temperatures. The discovery of these organisms forced scientists to reconsider the limits of life. Temperatures once thought impossible for life are now known to be merely difficult. They raise the possibility that life could exist in the hot interiors of planets and moons we once considered sterile, perhaps even in the upper layers of Venus's atmosphere, where temperatures and pressures are more moderate, or in volcanic regions on other worlds. Some bacteria eat electricity directly, without any organic molecules involved, a form of metabolism alien to most life. Geobacter species can consume electrons directly from metals, essentially feeding on electric currents, in a process sometimes called electrotrophy. Scientists are exploring their use in microbial fuel cells, batteries, and environmental cleanup of contaminated sites. These bacteria can extract energy from rust, from electrodes, from iron ore, from anything that can donate or accept electrons. They represent a fundamentally different metabolism from what most life uses. In nature, they live in soil and sediment, using iron or manganese as electron acceptors the way we use oxygen. In laboratories, they've been hooked up to electrodes and used to generate electricity from wastewater or organic waste. They can also work in reverse, accepting electrons from electrodes and using that energy to produce useful chemicals. Some researchers envision using these bacteria to create biological batteries, living sensors, or even to produce fuels like methane or hydrogen using electricity and carbon dioxide. Fungal networks connect forests in underground alliances that have been called the Wood Wide Web. Mycelium, the underground thread-like structures of fungi, link trees together across vast areas. These mycorrhizal networks, formed by fungi that form symbiotic relationships with plant roots, allow trees to share nutrients, send chemical warnings about insect attacks or disease, and even support struggling neighbors. A mother tree can recognize its offspring through chemical signatures and preferentially send them resources through the fungal network. Old trees support young saplings by sharing excess carbon. Healthy trees support sick trees. The forest is not a collection of individuals competing for resources,
but a cooperative network where the success of individuals depends on maintaining the health of the entire system. These networks can extend for kilometers, connecting hundreds of trees of different species. The fungi receive sugars from the trees and in return provide the trees with nutrients like phosphorus and nitrogen extracted from soil. Recent research suggests the networks may also transfer defensive chemicals, allowing trees that haven't yet been attacked by insects to prepare their defenses based on chemical warnings from trees that are being attacked. A single honey fungus in the Malheur National Forest in Oregon covers over 2,400 acres, nearly 10 square kilometers, and may be thousands of years old, potentially between 2,400 and 8,650 years old based on growth rate estimates. It is one of the largest and oldest living organisms on Earth by area, and possibly by mass as well. Most of its mass is underground, spreading through soil and rotting wood in an extensive network of mycelium. What we see as mushrooms are merely the fruiting bodies of this vast hidden organism. Like apples on a tree, they're just the reproductive structures, appearing seasonally when conditions are right. The fungus spreads slowly, expanding its network by a few centimeters per year as it consumes dead and sometimes living wood. It was discovered when forestry officials noticed patterns of tree death in the forest, and eventually traced them back through genetic analysis to a single massive organism. There may be even larger fungi elsewhere. Similar species have been found in other forests, though few have been fully mapped and aged. Plants can hear sounds in their environment and respond to them, though obviously not through ears as animals do. Studies show that plant roots grow toward the sound of running water, even when there's no moisture gradient to follow and no chemical signals present. In controlled experiments, plants exposed to recordings of water sounds grew their roots strongly in the direction of the speaker, while control plants showed no directional bias. Some plants also respond to the specific vibrations of chewing insects by releasing defensive chemicals, and they can distinguish between these vibrations and those caused by wind, rain, or other non-threatening sources. The vibrations created by a caterpillar chewing a leaf are different in frequency and pattern from those caused by wind, and plants appear to detect this difference through mechanoreceptors in their tissues. When exposed to recordings of chewing sounds, some plants increase production of chemical defenses even though no actual herbivores are present. This suggests plants have a primitive form of hearing, the ability to detect and respond to specific sound vibrations in ways that enhance their survival. Trees communicate through the air as well as through underground fungal networks. When a tree is attacked by insects, it releases volatile organic compounds, airborne chemical signals that drift on the wind. Neighboring trees detect these compounds through receptors in their leaves and preemptively boost their own defenses before they've even been touched, producing bitter tannins, toxins, or compounds that attract predators of the herbivores. The forest is constantly exchanging information through chemical signals. An acacia tree being browsed by giraffes will warn nearby acacias downwind, which increase their tannin production within minutes, making their leaves less palatable. Giraffes appear to have learned this, often feeding upwind or skipping trees between browsed ones. Some plants can even distinguish between chemical signals from related individuals and unrelated ones, responding more strongly to signals from genetic relatives, kin recognition in plants. The chemical signals can also travel through fungal networks below ground, providing multiple communication pathways between trees. The oldest living tree confirmed by direct counting of growth rings is over 5,000 years old. A bristlecone pine in California, nicknamed Methuselah, sprouted around 2832 BCE, making it older than the Egyptian pyramids, older than Stonehenge, older than the first cities in Mesopotamia. Its exact location in the White Mountains is kept secret to protect it from vandalism and excessive visitation. These trees survive in harsh, high-altitude environments between 2,900 and 3,400 meters elevation, where few other plants can compete. The extreme conditions, cold temperatures, short growing seasons, strong winds, poor rocky soil, and minimal precipitation ironically contribute to their longevity. Growth is so slow that wood is extremely dense and resistant to decay, insects, fire, and disease. Dead wood from bristlecone pines can remain intact for thousands of years after the tree dies. Growth rings in bristlecone pines provide one of the most accurate and long-reaching climate records available, allowing scientists to reconstruct precipitation patterns, temperature variations, and even volcanic eruptions going back over 9,000 years through living trees and dead wood fragments. There may be even older living trees. A clonal colony of quaking aspens called Pando in Utah is genetically identical and may be 80,000 years old, though the individual stems are much younger.
But there are organisms much older than any individual tree. A seagrass meadow of Posidonia oceanica in the Mediterranean near the Balearic Islands has been growing for at least 100,000 years through clonal reproduction, spreading as individual shoots extend and create new plants that are genetically identical to the original. This single organism, covering up to 15 kilometers of seafloor, predates anatomically modern humans, having already been ancient when our species evolved. This seagrass has survived the entire last ice age, sea level changes of over 100 meters, countless storms, and now faces threats from warming waters and coastal development. It grows incredibly slowly, perhaps advancing only a few centimeters per year, but over tens of thousands of years has created vast meadows that support rich ecosystems. These meadows are among the most valuable ecosystems on Earth, storing carbon, producing oxygen, stabilizing sediments, and providing habitat for countless species. The discovery of such ancient organisms challenges our concepts of individual and collective, life and death, and the timescales over which biological processes can operate.
Some plants can count and remember, performing simple calculations without any brain or neurons. The Venus flytrap counts the number of times its trigger hairs are touched before deciding whether to close its trap and begin digestion. One touch does nothing. It could be a raindrop, wind-blown debris, or a leaf falling from above. Two touches within approximately 20 seconds, and the trap snaps shut rapidly, completing the closing motion in less than 1/10 of a second, one of the fastest movements in the plant kingdom. But even after closing, the plant continues counting. More touches, 3, 4, 5, signal the plant that prey is struggling inside, triggering the release of digestive enzymes proportional to the amount of stimulation.
This counting mechanism requires memory at the cellular level, electrical signaling similar to nerve impulses in animals, and decision-making capability, all without a brain or neurons. The plant uses calcium ions and electrical potentials across cell membranes to track stimuli, similar to how neurons work in animals, but implemented in plant tissue. Action potentials spread through the trap when hairs are touched, and the plant must integrate these signals over time, remembering the first touch for up to 20 seconds to determine whether a second touch occurs. Slime molds, though completely brainless single-celled organisms when they exist as individual amoebas, can solve mazes, remember patterns, anticipate periodic events, and even recreate efficient transportation networks when they aggregate into multicellular forms. Scientists have used them to model transportation systems with surprising accuracy. In one famous experiment, researchers placed oat flakes, which slime molds feed on, at positions corresponding to cities around Tokyo, with the slime mold starting at Tokyo's location. The slime mold extended tendrils toward all the food sources, then gradually refined its network, reinforcing successful connections and abandoning inefficient paths. The final network strikingly resembled Tokyo's actual railway system, designed by human engineers optimizing for efficiency. The slime mold found an efficiently distributed, redundant network connecting all cities with minimal total length and reasonable directness of connections, a solution to a complex optimization problem that typically requires sophisticated algorithms. They accomplish this through simple local rules, extending pseudopods in all directions, reinforcing paths where food is found, and abandoning unproductive paths. Yet these simple rules produce sophisticated problem-solving behavior at the collective level. Slime molds can also learn to ignore harmless but irritating substances they initially avoid, demonstrating a form of habituation learning despite lacking anything resembling a brain. There are organisms that don't age in the conventional sense. They show no signs of increased mortality with age. Hydra, a tiny freshwater animal measuring just a few millimeters long, shows no signs of senescence or aging. Its cells constantly regenerate through continuous stem cell division, and under ideal conditions, it appears to live indefinitely. The Hydra replaces essentially its entire body every few weeks through constant cell turnover. Old cells die and are shed, while new ones are continuously generated. It doesn't accumulate cellular damage or lose function over time as most organisms do. Laboratory populations of Hydra have been maintained for years without any signs of aging or increased mortality. Studying these non-aging organisms may unlock secrets about aging and mortality. Why do most organisms age while a few apparently don't? What determines lifespan at the cellular level? Is aging an inevitable consequence of being alive, or is it a programmed process that could potentially be modified? Naked mole rats also show negligible senescence. Their mortality rate doesn't increase with age as it does in nearly all other mammals. A 20-year-old naked mole rat has approximately the same probability of dying as a 2-year-old, highly unusual for mammals. Understanding why might provide insights into aging mechanisms. The largest living structure on Earth by area is not a whale, a sequoia, or a coral reef. It's a fungus. Armillaria ostoyae in the Malheur National Forest in Oregon spans over 2,385 acres, about 965 hectares, or 9.65 square kilometers. It's been growing for an estimated 2,400 to 8,650 years, spreading slowly through forest soil, consuming dead wood, and occasionally attacking living trees, killing them and then feeding on the dead material. The fungus was discovered in the 1990s when forest pathologists investigating large-scale tree death in the area used aerial photos to map patterns of dying trees, then took samples and performed genetic analysis, showing that what appeared to be many individual fungi were actually one enormous organism connected by underground mycelial networks. The fungus grows slowly but steadily, expanding outward as its mycelium spreads through the soil. While it spans a huge area, its actual mass is difficult to determine, since much of it is microscopic threads distributed through soil and wood. It may weigh hundreds of tons, though exact figures are speculative. Antarctic icefish have evolved antifreeze proteins in their blood that prevent ice crystals from forming and allow them to survive in waters at -1.9 degrees Celsius, below the normal freezing point of fish blood. These glycoproteins don't prevent ice formation entirely. They can't lower the freezing point that much. Instead, they bind to tiny ice crystals that begin to form and prevent them from growing larger. The proteins adhere to ice crystal surfaces and block additional water molecules from joining, essentially capping the crystals at harmless sizes. Without this adaptation, the fish would freeze solid in their environment. Interestingly, Antarctic ice fish have also lost their red blood cells and hemoglobin over evolutionary time. They're the only vertebrates without hemoglobin. They rely on oxygen dissolved directly in their blood plasma, which works in the cold, oxygen-rich Antarctic waters, where oxygen solubility is higher than in warmer seas, but would be insufficient in warmer climates. Their hearts are unusually large to pump larger volumes of blood to compensate for lower oxygen carrying capacity. This combination of adaptations, antifreeze proteins, and loss of hemoglobin represents a unique evolutionary solution to extreme cold. Certain bacteria can survive on arsenic, substituting it for phosphorus in some molecules, a poison for most life used as a nutrient by these extremophiles. In 2010, researchers announced the controversial discovery of GFAJ1, a bacterium from Mono Lake, California, that could supposedly incorporate arsenic into its DNA when phosphorus was unavailable. The original claims were later disputed and scaled back after other scientists found flaws in the experimental methods. But the research sparked important discussions about biochemical flexibility and what life requires. While arsenic likely isn't fully replacing phosphorus in DNA as initially claimed, Some bacteria can tolerate extremely high arsenic concentrations and incorporate arsenic into other molecules. This research expanded our understanding of what life can tolerate and adapt to. If life can adapt to use unusual elements in some molecules, what other biochemistries might be possible on other worlds? Could life exist with fundamentally different biochemistry, using elements abundant on other planets but rare on Earth?
Some animals can survive being frozen solid, with ice filling their cells, and then revive when thawed. Wood frogs in Alaska and Canada freeze completely during winter in a remarkable adaptation to extreme cold. Their hearts stop beating. They stop breathing. Ice fills up to 70% of their body water. Yet they survive through producing high concentrations of glucose and other cryoprotectants that prevent lethal cell damage during freezing. When temperatures drop in autumn, the frogs prepare for freezing by producing glucose that reaches concentrations of up to 10 times normal levels.
This glucose permeates their cells and acts as a cryoprotectant, lowering the freezing point slightly, but more importantly, preventing the formation of large ice crystals that would puncture cell membranes. Ice forms first in extracellular spaces, and the frogs control where freezing occurs, using ice-nucleating proteins to initiate freezing in less critical areas. Once spring comes and temperatures rise, ice melts, cells resume function, the heart starts beating, breathing resumes, and the frog hops away as if awakening from sleep. They can survive repeated freeze-thaw cycles, remaining frozen for up to 8 months of the year in their northern range.
Similar adaptations have evolved independently in various insects, reptiles, and other organisms facing extreme cold.
Lichens are not a single organism, but a symbiotic partnership between fungi and photosynthetic partners, either green algae, cyanobacteria, or sometimes both, living together so intimately that they're given a single name and were thought to be individual organisms for thousands of years. They can survive in the most extreme environments, from Antarctic rocks at -50 degrees Celsius to desert stones at 70 degrees Celsius, from sea level to mountain peaks over 6,000 meters elevation. Some lichens are thousands of years old, among the oldest living things, growing less than a millimeter per year in harsh environments.
They can survive prolonged desiccation, drying out completely for years, and then resuming growth within hours when water becomes available. They withstand extreme UV radiation, temperature swings of over 100 degrees Celsius in a day in desert environments, and remarkably high levels of ionizing radiation. Lichens have even survived exposure to space. In experiments, lichen samples were attached to the outside of the International Space Station and exposed to the vacuum of space, cosmic radiation, UV radiation, and temperature extremes for weeks. After being returned to Earth, many of them survived and resumed normal photosynthesis and growth. This remarkable resilience makes lichens potential analogs for how life might survive on other worlds, or during transfer between planets on meteorites. There are bacteria living in radioactive waste and thriving in conditions that would be instantly lethal to all other known forms of complex life. Deinococcus radiodurans, nicknamed Conan the bacterium, can withstand radiation doses thousands of times higher than would kill a human, up to 5,000 times the lethal human dose. It can survive 1.5 million rads of radiation, whereas 500 to 1,000 rads would kill a human. It repairs its DNA almost as fast as radiation damages it, using redundant copies of its genome and highly efficient DNA repair mechanisms. Each cell contains 4 to 10 copies of its genome, so if radiation shatters the DNA into hundreds of pieces, the cell can use intact segments from other copies as templates to reconstruct the damaged DNA correctly. Scientists are studying this bacterium for potential use in cleaning up nuclear waste sites, breaking down toxic organic compounds in radioactive environments, and understanding the limits of DNA repair. No one knows why it evolved such extreme radiation resistance. There are no natural environments on Earth with radiation levels high enough to require this adaptation. One hypothesis is that the mechanisms evolved to resist extreme desiccation, which also causes DNA damage, and radiation resistance is a side effect. Certain species of ants have been farming fungus for over 50 million years in one of the most sophisticated examples of non-human agriculture.
Leafcutter ants don't eat the leaves they harvest. Watching them march in long lines, carrying leaf fragments many times their size, is watching farmers bringing in their harvest. They use the leaves to cultivate gardens of specialized fungus in underground chambers, which they then consume. This agricultural behavior evolved sometime between 45 and 60 million years ago. The ants have essentially domesticated the fungus, which has become dependent on the ants and is found nowhere else in nature. Neither can survive without the other. The fungus provides food for the ants, and the ants provide substrate and care for the fungus. The ants carefully tend their gardens, removing contaminants, maintaining optimal conditions for fungal growth, applying antibiotics they produce from bacteria growing on their bodies to prevent parasitic molds, and propagating the fungus when queens leave to establish new colonies. Each new queen carries a small sample of fungus in a special pouch in her mouth to start gardens in her new colony. The fungus has evolved specialized structures called gondolidia that grow on the end of fungal filaments and serve as food packets for the ants, structures that don't exist in related wild fungi. This mutualistic relationship is so ancient and sophisticated that it rivals human agriculture in complexity. Deep sea fish have evolved bizarre and sometimes nightmarish adaptations to survive in the absolute darkness and extreme pressure of the deep ocean. Anglerfish females use bioluminescent lures dangling from modified dorsal spines to attract prey in complete darkness. Males are drastically smaller, often less than 10% the size of females, and in some species, the male permanently fuses with the female in a parasitic relationship, becoming essentially a sperm-producing appendage. When a tiny male finds a female in the vast darkness, he bites her and releases an enzyme that digests the skin of his mouth and her body at the contact point, fusing them at the tissue level. Their circulatory systems join, and the male receives nutrients from the female's bloodstream while providing sperm when needed. Multiple males can fuse to a single female. The male gradually degenerates, losing eyes, fins, and most organs, except those needed to produce sperm. Other deep-sea fish, like gulper eels and viperfish, have enormous mouths and expandable stomachs, allowing them to consume prey larger than themselves, crucial in an environment where food is scarce and every meal opportunity must be seized. Some deep-sea fish have tubular eyes that point upward, scanning for the silhouettes of prey against the faint light filtering from above. These adaptations seem alien, but they're elegant solutions to the challenges of life in the largest and most extreme habitat on Earth. Some organisms produce natural antifreeze that's far more effective than any synthetic antifreeze we've engineered. The Arctic woolly bear caterpillar can survive being frozen at -70 degrees Celsius, cold enough to freeze carbon dioxide. It produces a mixture of proteins, polyols, and sugars that lower the freezing point of its body fluids and prevent ice crystal formation at the cellular level. These compounds don't just lower the freezing point, they also stabilize proteins and membranes during freezing. These caterpillars live in the Arctic, where summers are so short and cool that they can't complete their development in a single year. It takes them 7 to 14 years to complete their life cycle from egg to adult moth, spending most of each year frozen solid, then feeding frantically during the brief Arctic summer. They freeze and thaw repeatedly, perhaps 50 or more times over their lifetime before finally pupating. When you think about it, they spend more than 90% of their lives frozen, a radically different life history from temperate insects. Studying their antifreeze compounds has applications in preserving organs for transplantation, cryopreservation of cells and tissues, and protecting crops from frost damage. Some fish antifreeze proteins have already been incorporated into commercial ice cream to prevent ice crystal formation that creates grainy texture. Now we turn to landscapes that defy stillness, where the supposedly solid earth reveals its dynamic nature. Stones walk across the desert floor in Death Valley, leaving long trails behind them on the dry lake bed called Racetrack Playa. Some of these sailing stones weigh hundreds of pounds and have left tracks stretching for hundreds of meters across the flat surface. For decades, no one witnessed them move, despite countless vigils and camera traps. Theories ranged from high winds to magnetic fields to dust devils to pranks to, inevitably, aliens. The mystery was finally solved in 2014 when researchers installed GPS trackers on stones and time-lapse cameras around the playa. They discovered that movement requires a rare combination of conditions. The playa must flood slightly, creating a thin layer of water. Overnight temperatures must drop enough to form sheets of ice. The ice must be thin enough to move but thick enough to push stones, and morning winds must be strong enough to push the ice sheets, which drag the embedded stones along. The ice must be precisely the right thickness. Too thin and it breaks apart. Too thick and it doesn't move. The phenomenon occurs perhaps once every few years when conditions align perfectly. The stones can move at speeds up to several meters per minute while the ice is moving, then abruptly stop when the ice melts or breaks apart, leaving tracks that persist for years in the dry conditions. Fairy circles, mysterious bare patches in African grasslands, form perfect hexagonal patterns across thousands of square kilometers in Namibia and parts of Australia. From the air, the landscape appears polka-dotted with millions of nearly circular bare patches ranging from 2 to 12 meters in diameter, surrounded by rings of tall grass, arranged in remarkably regular patterns. Scientists have debated their cause for decades with fierce disagreements. Some researchers argue termites create them by eating vegetation in circular patterns around their underground nests, with the bare patches collecting water during rain that provides moisture for the termite colonies. Others propose that plants self-organize into these patterns through competition for water with no animals required, similar to Turing patterns in chemistry. Mathematical models show that plants competing for limited water can spontaneously create regularly spaced patterns where plants deplete water locally, creating bare zones, but water availability is better just beyond these zones, where grass grows vigorously. The circles can last for decades, appearing like living organisms. They're born small, grow, and eventually die as vegetation reclaims them, with a lifespan of 30 to 60 years typically. Recent research suggests both mechanisms may be at work. Termites and self-organization might both contribute to fairy circle formation. Their regular spacing and consistent size distribution suggest some underlying organizing principle we don't yet fully understand, making them one of nature's most beautiful unsolved mysteries. In Antarctica, blood falls oozes red liquid from a glacier, creating a crimson stain on the white ice, a sight so dramatic it looks otherworldly. The blood-red color comes from iron-rich saltwater trapped beneath Taylor Glacier for at least 1.5 million years. When this ancient water reaches the surface through cracks in the glacier and contacts oxygen, the dissolved iron oxidizes rapidly, turning a vivid blood red. Essentially, the water rusts as it emerges. The water is so salty it doesn't freeze even at -10 degrees Celsius, 3 to 4 times saltier than seawater, with salinity approaching saturation. This brine pocket trapped beneath the glacier represents an isolated ecosystem, sealed off from the surface world for over 1 million years. It hosts bacteria that survive without oxygen or sunlight, using iron and sulfur compounds for energy in a process similar to respiration, but using sulfate instead of oxygen. These microbes may represent one of the most isolated ecosystems on Earth, potentially evolving independently for over 1 million years. They're also an analog for potential life in similar environments elsewhere in the solar system, perhaps beneath the ice of Jupiter's moon Europa or Saturn's moon Enceladus, where subsurface oceans might harbor similar chemosynthetic ecosystems cut off from surface energy sources.
Forests are migrating poleward and upslope in response to climate change, though not fast enough to keep pace with warming. As climate warms, the geographical zones suitable for different tree species shift toward the poles and up mountains. Tree species are shifting their ranges. Seeds germinate farther from parent trees in directions that were previously too cold, and seedlings fail to establish in areas that have become too warm or dry. Studies tracking forest composition over decades show clear shifts. Tree lines are moving up mountains. The elevation where forest gives way to alpine vegetation is rising in mountain ranges worldwide. Boreal forests are creeping north into tundra in Alaska, Canada, and Siberia. But tree migration is slow.
Trees can't simply uproot and walk north. The population must shift through differential survival and reproduction, with new seedlings establishing at range edges while adults die without replacement at the other edge. Migration rates vary by species, but typically range from a few hundred meters to several kilometers per decade, much slower than the pace of climate change, which is effectively moving suitable climate zones poleward at rates of several kilometers per year in some regions. This mismatch between climate velocity and tree migration rates means many species may not be able to track suitable climates, leading to forest die-offs in some regions and only slowly advancing into newly suitable areas. Some species with heavy seeds that don't disperse far may be particularly vulnerable. Deserts can bloom overnight after rare rainstorms in phenomena called superblooms. Dormant seeds buried in deserts like the Atacama, Sonoran, or Mojave suddenly germinate and race through abbreviated life cycles. Within days, or sometimes just weeks, barren sand transforms into carpets of wildflowers, yellows, purples, reds, oranges, painting the landscape in spectacular displays that attract visitors from around the world. The seeds can wait decades for the right conditions, programmed by evolution to germinate only when soil moisture reaches critical thresholds that indicate enough water for completing their life cycle. They have thick protective seed coats and chemical germination inhibitors that prevent premature sprouting. Only sustained rainfall that soaks deep into the soil and washes away these inhibitors triggers germination. The plants must then flower, produce seeds, and complete their entire life cycle within the brief window before the desert dries again, sometimes just a few weeks. After flowering, the plants die and disperse seeds, which enter dormancy and may wait another decade or more for the next rain. The timing, extent, and species composition of superblooms vary unpredictably, depending on the amount and timing of rainfall. Some of the most spectacular blooms occur after El Niño winters bring unusual amounts of rain to typically arid regions. These blooms are reminders that deserts aren't lifeless. They're ecosystems where life waits patiently for opportunity. The Atacama Desert in northern Chile is the driest place on Earth. Some regions have experienced no recorded rainfall in human history. Weather stations have operated for decades without detecting a single drop of measurable precipitation. Some areas may have gone without rain for 400 years or more, based on historical records and geological evidence. Average rainfall in the driest parts is less than 1 millimeter per year, and some locations may receive rain only a few times per century. Yet life persists even here. Microbes survive by harvesting moisture from fog that rolls in from the Pacific Ocean on perhaps 40 to 100 days per year. Lichens cling to rocks, absorbing water from morning dew formed when fog condenses. In the few locations where underground water sources reach the surface, oases support vegetation. Cacti and other specialized plants store water from occasional fog or rare rain. Some parts of the Atacama are so dry and sterile that NASA uses them to test Mars rovers, considering the landscape the closest terrestrial analog to Martian conditions. Soil in the Atacama's driest regions lacks detectable organic compounds and harbors virtually no microbial life, unusual for Earth, where microbes are found almost everywhere else. This extreme aridity results from the rain shadow of the Andes to the east, the cold Humboldt current offshore that creates atmospheric stability, and the South Pacific high-pressure system that produces persistent descending air that inhibits cloud formation. Beneath the Sahara lies an ancient aquifer system, the Nubian Sandstone Aquifer System, one of the largest known fossil water reserves on Earth. This massive underground water reserve extends beneath parts of Egypt, Libya, Chad, and Sudan, covering about 2 million square kilometers. It holds an estimated 150,000 cubic kilometers of water, enough to fill Lake Superior 7 times over. This water fell as rain over 10,000 to 25,000 years ago during the African humid period, when the Sahara was green. It seeped into porous sandstone layers and became trapped beneath impermeable rock layers. This fossil water is being extracted for agriculture at rates far exceeding natural recharge, which is essentially zero in the current arid climate.
Libya's Great Man-Made River Project, sometimes called the world's largest irrigation project, pumps water from this aquifer through a network of enormous pipes to supply cities and farms. Satellite imagery shows expanding circular farm plots, center pivot irrigation systems drawing on ancient water, creating green circles in the yellow desert. But this is mining water, not sustainable use. Once the fossil water is exhausted, which could happen within decades to centuries depending on extraction rates, it won't be replenished. The aquifer is a finite memory of a wetter past being slowly depleted. Its depletion will have profound consequences for the millions of people who have come to depend on it.
Rivers can disappear entirely, never reaching the sea. The Okavango River in Africa ends in a vast inland delta in Botswana, spreading across 15,000 square kilometers of the Kalahari Desert and eventually evaporating or seeping into the sand. The water never reaches the ocean. Instead, it creates a seasonal wetland that supports incredible biodiversity. Elephants, hippos, crocodiles, buffalo, countless antelope species, and over 400 bird species. The delta's flooding is paradoxical. It occurs during the dry season. Rain falls in the Angolan highlands between January and March, then takes 4 to 6 months to flow the 1,200 kilometers down the Okavango River. By the time the flood reaches the delta, usually between June and August, Botswana is experiencing its dry season, making the flood's arrival crucial for wildlife. The delta expands during flood season from about 6,000 square kilometers to 15,000 square kilometers as water spreads across the flat landscape through a labyrinth of channels, lagoons, and flooded grasslands. As the flood recedes, animals concentrate around remaining water sources, creating spectacular wildlife viewing opportunities. The Okavango Delta is one of the world's largest and most pristine inland delta systems, a UNESCO World Heritage Site, and a vivid example of how water can create life in the midst of desert.
Some rivers run backward during extreme tides or floods, reversing their normal flow. The tidal bore phenomenon, a wave that travels upstream against the river's current, can push saltwater dozens of kilometers inland and, in extreme cases, temporarily reverse flow direction. The Qiantang River in China has one of the largest tidal bores, with waves reaching up to 9 meters high during autumn-spring tides, traveling upstream at speeds up to 40 kilometers per hour with a roaring sound audible from kilometers away. The bore attracts surfers brave enough to ride it, and spectators who watch from, hopefully, safe distances, though the bore has claimed lives when viewers were caught by unexpected surges. The Amazon River also experiences a tidal bore called the Pororoca that can travel over 800 kilometers upstream. During the spring tides in the Atlantic, a wall of water surges up the river mouth, creating waves suitable for surfing and temporarily overwhelming the river's downstream flow. In some rivers, extreme floods can create upstream flows through backwater effects, where downstream constrictions or confluences with other rivers cause water to back up and flow upstream in tributaries. The Mississippi River has experienced this during major floods. The Amazon rainforest creates its own weather through transpiration, the release of water vapor from plant leaves. With over 390 billion trees covering 5.5 million square kilometers, the Amazon releases an enormous amount of moisture into the atmosphere. Large trees can transpire hundreds of liters of water per day, and collectively, the forest releases about 20 billion tons of water vapor into the atmosphere daily, more than the Amazon River discharges into the Atlantic. This moisture forms clouds that produce rain, which falls back on the forest, is absorbed by trees, and transpires again in a continuous cycle. Scientists call this recycling of moisture flying rivers in the atmosphere, and estimate that air masses passing over the Amazon can recycle water 5 to 6 times before it finally flows out of the basin.
This means rain falling in the western Amazon has often fallen and evaporated multiple times as it traveled across the continent from the Atlantic. Deforestation disrupts this cycle in potentially catastrophic ways. As trees are removed, less moisture enters the atmosphere, potentially reducing rainfall not just locally, but thousands of kilometers away. Some models suggest that extensive deforestation could trigger a tipping point where the Amazon transitions from rainforest to savanna, with cascading effects on global climate.
The forest essentially creates the very conditions it needs to survive. Removing too much of it could make it impossible for the rest to regenerate.
The Amazon depends on dust from the Sahara in a remarkable transcontinental connection. Nutrients from a distant desert sustaining the world's largest rainforest. Every year, trade winds carry roughly 27 million tons of Saharan dust across the Atlantic Ocean, a journey of over 5,000 kilometers over the ocean. About 15% of this dust, roughly 4 million tons, is deposited on the Amazon basin. This dust contains phosphorus, iron, and other minerals eroded from the Baudelaire Depression in Chad, an ancient lakebed that was once Lake Mega-Chad during wetter periods. The Amazon's highly weathered soils are naturally poor in phosphorus, which is gradually leached away by heavy rains and carried to the ocean by rivers. The Saharan dust replenishes this loss, delivering about 22,000 tons of phosphorus annually, almost exactly compensating for phosphorus lost to rivers. Without this nutrient subsidy from Africa, the Amazon would be significantly less productive. Satellite images track these massive dust plumes crossing the Atlantic, visible as tan clouds against the blue ocean. The connection illustrates how Earth systems are interconnected across vast distances. Changes in African climate affecting dust production could impact Amazon productivity on the other side of the planet.
It's also a reminder that some desert dust is transported globally, affecting air quality, ocean productivity, snowmelt rates, and even hurricane formation through its effects on atmospheric properties. Caves can be enormous, far larger than most people imagine. The Hang Son Dong Cave in Vietnam is so large it has its own weather system, complete with clouds that form near the ceiling when moist air from the jungle outside meets cooler air in the cave. At its largest, the cave measures over 200 meters high, 150 meters wide, and stretches for at least 5 kilometers, though some sections remain unexplored. It could fit a 40-story skyscraper with room to spare. The cave was unknown to the outside world until 1991, when a local man discovered the entrance while seeking shelter from a storm, and he couldn't relocate it for nearly 20 years. It was only fully explored in 2009 by British cavers. Inside, stalagmites tower like buildings, some over 80 meters tall, among the tallest cave formations known. An underground river carved the cave over millions of years, and sections of the ceiling have collapsed, creating sinkholes that allow sunlight to penetrate. These collapsed sections have their own microclimate, where jungle vegetation grows inside the cave, underground forests with trees up to 30 meters tall, receiving light from sinkholes above. Exploring Sondong requires technical caving skills, river crossings, and climbing enormous cave formations. Only a few hundred people have entered it since its discovery. There are underground rivers and lakes that have never seen sunlight, hosting unique species that evolved in total darkness. These subterranean ecosystems exist in aquifers, flooded cave systems, and porous rock layers beneath the surface. They contain unique species that have evolved in isolation: translucent fish without eyes or pigmentation, blind salamanders, colorless crustaceans, and other troglobites specially adapted to perpetual darkness. These animals have lost eyes and pigmentation as useless traits in an environment without light. They navigate by touch, chemical sensing, and lateral line systems that detect water movements.
Many have slowed metabolism and long lifespans compared to surface relatives, adaptations to the food-poor cave environment. In some cases, related species on the surface went extinct while their cave-dwelling relatives survived, making them living fossils. The devil's hole pupfish, for instance, lives in a single desert pool in Nevada connected to deep aquifer systems. It may be the most restricted range vertebrate on Earth, surviving in a habitat measuring roughly 3 meters by 6 meters at the surface, though the pool continues deep underground. These isolated subterranean ecosystems are vulnerable to groundwater pollution and aquifer depletion.
Cenotes in Mexico's Yucatan Peninsula are sinkholes connected to vast underground river systems carved through the limestone bedrock. The ancient Maya considered them sacred portals to Xibalba, the underworld, and archaeological evidence shows they were used for ceremonies and sometimes sacrifices. Underwater archaeologists and cave divers have discovered ancient human remains, pottery, jewelry, and other artifacts in cenotes, along with bones of extinct megafauna, including gomphotheres, elephant relatives, giant ground sloths, and saber-toothed cats that fell into sinkholes thousands of years ago. Some of the oldest human remains in the Americas have been found in flooded cenotes, including the 13,000-year-old skeleton of Naya, a teenage girl whose remains have provided insights into the peopling of the Americas. The underwater cave systems beneath the Yucatan are among the longest in the world. Sistema Sac Actun, for instance, extends over 370 kilometers of explored passages. Cave divers continue to discover new connections between cenotes, gradually mapping this hidden underwater world. The fresh water flowing through these caves eventually reaches the ocean, creating unique mixing zones where freshwater and saltwater meet, with a visible boundary called the halocline, where different densities and refractive indices create a mirror-like effect underwater.
Quicksand is real, though it doesn't work like the movies portray. You can't sink completely and vanish. Human bodies are less dense than quicksand, so you'll float rather like in water, typically sinking only to about waist or chest depth before buoyancy stops you. The danger isn't drowning in sand, but getting stuck and being unable to escape before environmental exposure, incoming tides in coastal areas, or exhaustion takes its toll. Quicksand forms when water saturates sand or fine sediment, reducing friction between grains to nearly zero. The sand behaves like a liquid, unable to support weight.
If you struggle or make quick movements, you create a vacuum beneath you as water flows sluggishly to fill gaps, and this suction makes it harder to pull yourself out. Trying to yank a leg out quickly can require force equivalent to lifting a car. The key to escaping is to move slowly and deliberately. Lean back to distribute your weight and increase buoyancy, and gradually wiggle your legs to allow water to flow around them and break the suction. Then swim towards solid ground. Quicksand can form anywhere water and loose sand or silt coincide. Riverbeds, beaches, near underground springs, or after earthquakes when ground becomes liquefied. It's more of a nuisance than a death trap, but people have died when stuck in quicksand in areas where tides come in, or when unable to escape and exposure to elements proves fatal.
There are places where gravity feels different from the global average, variations large enough to measure with precision instruments, though too small for humans to notice directly. Hudson Bay in Canada has slightly weaker gravity than most of Earth, about 0.003% less than normal. Two factors contribute to this. The Laurentidae ice sheet that covered the region during the last ice age, up to 3 kilometers thick, compressed the mantle beneath it. The ice melted about 10,000 years ago, but the mantle is still slowly rebounding upward, a process called glacial isostatic adjustment. The region is rising about 1 centimeter per year as the mantle recovers its shape.
During this rebound, there's a mass deficit, less material overhead, resulting in weaker gravity. Additionally, the centrifugal effect of Earth's rotation creates an equatorial bulge, making the Earth wider at the equator than at the poles. Locations farther from the equator are closer to Earth's center of mass, which would normally increase gravity, but this is more than offset by the missing mass from the ice sheet. The gravity anomaly was precisely measured by the GRACE satellites, which detected tiny variations in their orbital speed caused by gravity differences as they passed over different regions. Similar gravity anomalies exist at other locations worldwide, caused by underground mass variations, mountain roots extending deep into the crust, dense ore bodies, or depleted aquifers. Earth has natural nuclear reactors that operated billions of years ago, the only known natural fission reactors in the solar system. 2 billion years ago, in what is now Gabon, West Africa, uranium deposits became concentrated enough to sustain nuclear chain reactions. These natural reactors ran intermittently for hundreds of thousands of years, producing heat and radiation just like human-built reactors. They were discovered in 1972 when French scientists analyzing uranium ore from Gabon noticed that the uranium-235 isotope ratio was depleted compared to natural uranium found elsewhere, indicating that fission had occurred. They eventually identified 16 sites where natural reactors operated.
These reactors only formed because conditions were perfect. Uranium ore was enriched to about 3% U-235, similar to reactor fuel. Groundwater percolated through the ore, acting as a neutron moderator to sustain chain reactions, and the geological setting concentrated uranium sufficiently. The reactors were self-regulating. When water heated and turned to steam, the chain reaction slowed without the moderator. When the rock cooled and water returned, reactions resumed.
Nothing like this could happen today, because uranium-235 has a half-life of 700 million years, and Earth's natural uranium has decayed from about 3% U-235 2 billion years ago to only 0.7% today, too dilute to sustain chain reactions even with optimal conditions. These natural reactors have been studied extensively to understand how fission products migrate through rock, providing insights for nuclear waste disposal.
The world's largest cave crystal formations are in Mexico's Cave of Crystals, discovered in 2000 in the Nika mine. Selenite, a crystalline form of gypsum, crystals, some over 11 meters long, 4 meters in diameter, and weighing up to 55 tons, grew in mineral-rich water kept at a stable 58 degrees Celsius by magma below. The crystals grew extremely slowly, over approximately 500,000 years, with growth rates of perhaps micrometers per year, producing crystals of exceptional size and clarity. The chamber was so hot and humid, up to 58 degrees Celsius with near 100% humidity, that explorers could only survive inside for 5 to 10 minutes, even with specialized cooling suits filled with ice and cooled breathing apparatus.
Without protection, a person would die within minutes from hyperthermia. The combination of heat and humidity prevents evaporative cooling, sweating, and body temperature rises rapidly to lethal levels. The mine that contained the cave was dewatered for mining operations, exposing the crystals. But when mining ceased, the decision was made to allow the mine to flood again to preserve the crystals in their original environment. In dry air, the crystals would gradually dehydrate and deteriorate, becoming opaque and eventually crumbling. Submerged again in mineral-rich water, the crystals are preserved, though now inaccessible except to specialized diving expeditions.
The cave represents an extraordinary geological phenomenon, crystal growth on a scale rarely seen.
Earth bears scars from ancient asteroid impacts, craters that have survived for billions of years despite erosion and geological activity. The Vredefort impact structure in South Africa, over 2 billion years old, is the largest confirmed impact crater on Earth. The original crater was roughly 300 kilometers in diameter, though billions of years of erosion have reduced the visible remains. When the asteroid struck, estimated at 10 to 15 kilometers in diameter, it created an enormous impact crater with a central uplift and multiple ring structures.
The impact was so powerful it created shock waves that melted rock, created unique high-pressure minerals that only form under extreme conditions, and left permanent deformations in geological layers visible today. The rocks at Vredefort have been tilted vertical, folded, and faulted by the impact forces. The energy released was equivalent to billions of nuclear weapons, likely enough to cause global environmental catastrophe. The impact occurred before complex life evolved, but it would have significantly affected the biosphere that existed at the time, potentially boiling off portions of the ocean and ejecting material into space.
Studying ancient impact structures teaches us about impact processes, how impacts affect planetary crusts, and the role impacts have played in Earth's history. They're also reminders that Earth orbits through a shooting gallery. Impacts are not just ancient history, but ongoing processes that have and will continue to shape our planet.
Impact events have repeatedly reshaped life on Earth. Mass extinctions, evolutionary opportunities, and fundamental changes to the biosphere. The asteroid that killed the non-avian dinosaurs 66 million years ago left a crater 180 kilometers wide beneath the Yucatan Peninsula, known as the Chicxulub crater. Named after a nearby town, the crater itself is buried under kilometers of sediment and only detectable through geophysical surveys. The impactor was roughly 10 to 15 kilometers in diameter, traveling perhaps 20 kilometers per second when it struck. The impact vaporized the asteroid and the rock it struck, creating a fireball that radiated intense heat across the region. Ejecta fell globally, starting wildfires across multiple continents.
A tsunami hundreds of meters high swept across the Gulf of Mexico and Caribbean, but the global effects were even more catastrophic. The impact ejected so much material into the atmosphere that it blocked sunlight for months to years, creating an impact winter. Global temperatures plummeted by perhaps 20 to 30 degrees Celsius. Photosynthesis stopped, plants died. Herbivores starved. The food chain collapsed from the bottom up. 75% of all species went extinct, including all non-avian dinosaurs, pterosaurs, marine reptiles, and many other groups.
But the extinction created opportunities. The disappearance of dominant groups allowed mammals, which had been small and relatively insignificant for over 100 million years, to diversify and eventually give rise to primates and humans. Without that asteroid impact, dinosaurs might still dominate, and humans would never have evolved. Other impact events throughout Earth's history have similarly shaped evolution, suggesting that impacts are not just destructive, but creative forces, opening niches and driving evolutionary innovation. Some rocks remember the magnetic field orientation when they formed, a remarkable property that allows us to study Earth's past. Paleomagnetism is based on the fact that certain minerals containing iron, like magnetite, align with Earth's magnetic field as they crystallize from cooling magma or settle out of water. Once the rock solidifies or sediment lithifies, the magnetic orientation is locked in place, creating a permanent record of the magnetic field's direction and intensity at the time and location of formation. By measuring this remnant magnetism in rocks of different ages from different locations, scientists have reconstructed plate tectonics over hundreds of millions of years, documented magnetic field reversals going back billions of years, and even determined paleolatitudes, how far from the equator a rock formed based on the inclination angle of its magnetic signature. This is how we know continents have drifted. Ancient rocks in North America have magnetic signatures indicating they formed near the equator, even though they're now at mid-latitudes. Oceanic crust records magnetic striping symmetrical around mid-ocean ridges, alternating bands of normal and reversed polarity as new seafloor forms during periods of normal and reversed field orientation. This magnetic striping was crucial evidence for seafloor spreading and plate tectonics. Rocks essentially remember where they formed and what Earth's magnetic field was like, preserving information for billions of years. There are places where compasses spin uselessly, unable to find north. Near the magnetic poles, which don't coincide with the geographic poles, compass needles try to point straight down or up in the southern hemisphere, rather than horizontally, rendering them ineffective for navigation. The magnetic poles wander significantly over time, moving tens of kilometers per year. The North Magnetic Pole is currently drifting rapidly from Canadian Arctic toward Russia at about 55 kilometers per year, much faster than the historical average of about 15 kilometers per year. This accelerating drift has required frequent updates to navigation charts, aviation systems, and even smartphone compass apps. Scientists aren't entirely certain why the drift has accelerated, but suspect changes in the flow patterns of liquid iron in Earth's outer core. Some researchers speculate we might be heading toward a magnetic reversal, though predicting reversals is currently impossible. During reversals, the field weakens significantly and becomes more complex, potentially with multiple poles, before settling into a new stable configuration. Geologic evidence suggests we're overdue for a reversal, based on the average spacing between reversals. But this is hardly a reliable predictor. The interval between reversals varies from tens of thousands to tens of millions of years. Compasses would become unreliable during a reversal, which would be inconvenient, but the more serious concern is the weakened magnetic field during the transition, which would increase radiation exposure from cosmic rays and solar storms. Earth's rotation causes the Coriolis effect, which deflects moving objects to the right in the northern hemisphere and to the left in the southern hemisphere, a consequence of rotating frames of reference that has profound effects on weather and ocean currents. This is why hurricanes, typhoons, and cyclones spin counterclockwise north of the equator and clockwise south of it. It's why ocean currents curve instead of flowing straight. It's why long-range artillery must account for the Coriolis effect. A shell fired 30 kilometers will be deflected significantly if not compensated for. The Coriolis effect is zero at the equator and maximum at the poles, which is one reason hurricanes don't form directly on the equator. They require Coriolis deflection to begin rotating. The effect increases with the speed and distance of movement. For everyday human-scale movements, the Coriolis effect is negligible, despite persistent myths about water draining in different directions in sinks in different hemispheres. Direction in sinks is determined by basin shape and initial water motion, not the Coriolis effect, which is far too weak at that scale. But for large-scale atmospheric and oceanic flows, the Coriolis effect is fundamental, shaping weather patterns, ocean gyres, and climate. It's a constant reminder that we live on a spinning planet. Even though we can't feel the motion directly, we see its effects everywhere in Earth's fluid systems. Earth is not an isolated island in the void. It is intimately connected to the cosmos in ways both beautiful and profound, constantly exchanging matter and energy with space. Every day, Earth gains about 100 tons of material from space through the continuous rain of cosmic dust and meteoroids. Cosmic dust, micrometeorites, typically under a millimeter in size, and occasional larger meteorites constantly fall onto Earth. Over billions of years, this influx has contributed significantly to our planet's mass, hundreds of millions of tons since Earth formed. This extraterrestrial material carries elements and potentially organic molecules. Some of this dust may contain or have contained the building blocks of life. Meteorites have been found carrying amino acids, the building blocks of proteins, sugars, lipids, and even nucleobases, the building blocks of DNA and RNA. The Murchison meteorite, a carbonaceous chondrite that fell in Australia in 1969, contained over 70 different amino acids, including many not found in Earth life, proving that complex organic chemistry occurs in space. Other meteorites contain organic compounds like polycyclic aromatic hydrocarbons, alcohols, and other complex molecules. Panspermia, the theory that life's ingredients, or even primitive life itself, might have come from space, perhaps originating elsewhere and being transported to Earth on meteorites or comets, remains a compelling possibility that has gained respectability as we've discovered how much organic chemistry occurs throughout the solar system and beyond. While we have no definitive evidence that life itself arrived from space, the chemical precursors certainly did, and Earth's early oceans may have been enriched with organic compounds from space, providing raw materials for life's origin. The auroras, the northern and southern lights, aurora borealis and aurora australis, are one of Earth's most beautiful phenomena, caused by solar wind colliding with our magnetic field. The sun constantly emits charged particles, primarily electrons and protons, that stream outward as the solar wind, traveling at speeds of 400 to 800 kilometers per second. When these charged particles encounter Earth's magnetic field, they're guided along magnetic field lines toward the poles. As they spiral down toward Earth, they collide with atmospheric gases at altitudes of 100 to 500 kilometers. These collisions excite atoms and molecules, transferring energy that's subsequently released as light when the atoms return to lower energy states. Oxygen produces green light at lower altitudes, around 150 to 150 kilometers, and rare red light at higher altitudes, above 200 kilometers. Nitrogen produces blue and purple colors. The specific colors and altitudes depend on which gas is being excited, how much energy the collision transfers, and atmospheric density at different altitudes. Auroras occur in oval zones around the magnetic poles, expanding toward the equator during intense solar storms, when the solar wind is particularly strong. During extreme space weather events, coronal mass ejections that send billions of tons of solar material toward Earth, auroras can be visible at remarkably low latitudes, even in the tropics in the most extreme historical events. The auroras are visual evidence of Earth's magnetic field protecting us from the solar wind. Without this shield, the solar wind would erode our atmosphere, as it did on Mars. Auroras sometimes produce sounds, though this was considered folklore until recently confirmed by scientific investigation. Some observers report hearing faint crackling, whooshing, or rustling noises during intense auroral displays, though these sounds have proven extremely difficult to record and study scientifically. For centuries, indigenous peoples in polar regions described aurora sounds in their oral traditions, but scientists were skeptical because auroras occur at altitudes of 100 to 500 kilometers, far too high for sound waves to travel downward through the increasingly thin atmosphere to reach ground level. Recent research suggests the sounds likely occur through a different mechanism. When charged particles associated with auroral activity interact with temperature inversion layers in the atmosphere much closer to the ground, around 70 to 75 meters altitude, they can create electrostatic discharges that produce audible sound through sparking from objects like trees, buildings, or even hair. These discharges would be rare, requiring specific atmospheric conditions with temperature inversions that trap charged particles near the surface. The sounds are extremely rare and localized, which explains why most people who see auroras never hear them, while occasional observers under specific conditions do. The phenomenon remains somewhat controversial and incompletely understood, partly because it's so difficult to study, requiring simultaneous occurrence of intense auroras, temperature inversions, appropriate atmospheric conditions, observers in the right locations, and recording equipment to capture the transient sounds.
Earth's magnetosphere has a long tail extending over 1 million kilometers away from the Sun, more than 3 times the distance to the Moon. As solar wind pushes against our magnetic field, it compresses the magnetosphere on the sunward side to about 10 Earth radii, roughly 60,000 kilometers, but stretches it into an elongated magnetotail on the night side. This tail extends to at least 200 Earth radii, about 1.3 million kilometers, and possibly much farther. The exact length is difficult to determine because the tail becomes increasingly diffuse with distance. The Moon sometimes passes through Earth's magnetotail during its orbit, briefly exposing the lunar surface to particles from Earth's upper atmosphere rather than direct solar wind.
The magnetotail stores energy from the solar wind through magnetic field line stretching. This energy is occasionally released in magnetic reconnection events, when stretched field lines snap back, releasing stored energy and accelerating particles toward Earth, creating substorms that intensify auroras and can disrupt satellites and power grids. Understanding the magnetotail's behavior is crucial for space weather prediction and protecting technological systems from solar storms.
Cosmic rays constantly bombard Earth from all directions. High-energy particles accelerated to near light speed by supernova explosions, collisions between galaxies, and other violent cosmic events. These particles, primarily protons, but also heavier atomic nuclei, travel through space for millions of years before randomly encountering Earth. When cosmic rays collide with atmospheric molecules at the top of the atmosphere, they create cascades of secondary particles, called air showers. A single high-energy cosmic ray can produce billions of secondary particles cascading through the atmosphere like an inverted tree, spreading over areas of several square kilometers by the time they reach the surface. Some of these particles, primarily muons, which are heavy cousins of electrons, penetrate deep underground and can be detected in mines and underwater detectors. Earth's magnetic field deflects many lower-energy cosmic rays, particularly at the equator, where field lines are horizontal, but the highest energy cosmic rays penetrate regardless. Cosmic ray flux varies with solar activity. During solar maximum, when the sun's magnetic field is strong, fewer cosmic rays reach Earth.
During solar minimum, more penetrate. Some researchers believe cosmic rays influence cloud formation by ionizing air molecules, creating charged particles that can act as condensation nuclei around which water droplets form.
If this effect is significant, cosmic rays might play a subtle role in climate, with galactic cosmic ray flux varying based on solar activity, and potentially even on longer timescales as our solar system orbits through regions of the galaxy with different cosmic ray density. Cosmic rays can flip bits in computer memory, causing random glitches in electronics, an increasingly important issue as electronics become smaller and more vulnerable. Called single event upsets, SEUs, these occur when a high-energy particle strikes a memory chip and deposits enough charge to change a bit from 0 to 1, or vice versa. A single cosmic ray, or more commonly a secondary particle from a cosmic ray air shower, striking a sensitive region of a microchip can cause unpredictable behavior. In aircraft flying at high altitudes where radiation exposure is greater and atmospheric shielding is less, SEUs are more common. In spacecraft beyond Earth's protective magnetosphere, they're a major concern, requiring error correction codes and radiation-hardened electronics. But even at ground level, cosmic rays can cause problems. Some election machine errors, video game glitches, including speedrunners' famous Super Mario 64 upwarp glitch, where cosmic rays were proposed as a possible explanation for a bit flip that allowed Mario to warp through the level, and computer crashes have been tentatively attributed to cosmic rays. As electronics become smaller, transistors shrink, and the amount of charge needed to flip a bit decreases, making them more vulnerable to cosmic ray interference. Modern computers include error-correcting memory and redundancy to catch and fix such errors, but they remain an unavoidable consequence of operating electronics in an environment with constant low-level radiation from space. Earth's atmosphere protects us from the vast majority of meteoroids that enter it daily. About 25 million meteors, what we commonly call shooting stars, enter Earth's atmosphere every day, though most are tiny dust-sized particles. They typically burn up 80 to 100 kilometers above the surface through friction with air molecules. The meteor itself doesn't catch fire. Rather, friction heats the air in front of it to thousands of degrees, creating a glowing plasma that we see as a streak of light lasting only seconds. Most meteors are created by particles smaller than a grain of sand, released from comets as they pass through the inner solar system and orbit along the comet's path. When Earth passes through these debris streams, we experience meteor showers with predictable timing, like the Perseids in August or the Geminids in December. On a clear night, away from light pollution, you can typically see 5 to 10 sporadic meteors per hour. During meteor showers, rates can increase to dozens or even hundreds per hour during exceptional displays. Larger objects, meteorites, that survive to reach the surface are much rarer, perhaps a few thousand per year globally, most falling into oceans or unpopulated areas and never recovered. Occasionally, large meteors explode in the atmosphere with devastating effect. The Tunguska event on June 30, 1908 in Siberia remains the largest impact event in recorded history. An object estimated at 50 to 100 meters in diameter, likely a fragment of a comet or asteroid, entered the atmosphere and exploded about 5 to 10 kilometers above the ground. The explosion, equivalent to 10 to 15 megatons of TNT, roughly 1,000 Hiroshima bombs, flattened 2,000 square kilometers of forest, 80 million trees knocked down in a radial pattern from the blast center. Witnesses 60 kilometers away were knocked off their feet. The shockwave was detected by barometers as far away as Britain, circling the globe twice. Night skies glowed for several nights afterward across Europe and Asia, bright enough to read by at midnight in London, from dust and ice crystals injected into the upper atmosphere. If the explosion had occurred over a populated area rather than remote forest, the death toll would have been catastrophic. No crater was formed because the object exploded in the air, but the explosion was more destructive than a surface impact of the same energy would have been, since the blast wave spread out over a larger area. The Tunguska site wasn't scientifically investigated until decades later due to its remoteness and the chaos of early 20th century Russian history. When expeditions finally reached the area in 1927, they found the devastation still clearly visible, with fallen trees radiating outward from the epicenter and the central area where trees remained standing but stripped of branches. The Chelyabinsk meteor in 2013 provided the most thoroughly documented meteor impact in history, thanks to ubiquitous dashboard cameras in Russia. On February 15, 2013, an object about 20 meters in diameter entered the atmosphere over Russia at over 60,000 kilometers per hour, about 60 times the speed of sound. It exploded about 30 kilometers above the ground, with energy equivalent to about 500 kilotons of TNT, roughly 30 Hiroshima bombs. The shockwave injured over 1,500 people, mostly from shattered glass in buildings that couldn't withstand the sudden pressure change. Thousands of buildings were damaged. The event was captured by hundreds of dashboard cameras from multiple angles, providing unprecedented data about how asteroids behave as they enter the atmosphere. Scientists analyzed the videos frame by frame to reconstruct the meteor's trajectory, composition, and breakup sequence. The object fragmented as it descended due to atmospheric pressure overcoming its structural strength, a process called aerodynamic ablation. Fragments scattered across a wide area, with the largest recovered piece weighing 654 kilograms, pulled from a frozen lake. The Chelyabinsk event was a reminder that impacts are not ancient history. Objects this size strike Earth roughly once every 60 to 100 years on average, and larger ones hit less frequently. The event sparked renewed interest in planetary defense and asteroid detection programs. Earth has quasi-satellites, asteroids in peculiar orbits that appear to orbit Earth when viewed from our planet, though they're actually in resonance with Earth's orbit around the Sun. The most famous is 3753 Kruithne, discovered in 1986 and recognized as a quasi-satellite in 1997. From Earth's perspective, Kruithne appears to trace a bean-shaped orbit around us over the course of a year. But from the Sun's perspective, both Earth and Kruithne orbit the Sun in elliptical paths, with Kruithne's orbit locked in resonance with Earth's through gravitational interactions.
Kruithne never gets closer than about 12 million kilometers, roughly 30 times the Moon's distance. So it's not a true moon and has no significant gravitational effect on Earth. Its quasi-satellite relationship is temporary in astronomical terms, lasting only about 5,000 years before and after the current period. But it's been our companion for millennia and will remain so for millennia more. Several other quasi-satellites have been discovered, coming and going over thousands of years as orbital resonances sift. Earth also has true temporary satellites occasionally, small asteroids a few meters across that get gravitationally captured into orbit around Earth for a few months to a few years before escaping again.
One such object, designated 2006 RH-120, orbited Earth from September 2006 to June 2007 before returning to solar orbit. There are thousands of pieces of space debris orbiting Earth, a growing hazard to operational satellites and human spaceflight. Defunct satellites, spent rocket stages, paint flecks, frozen coolant droplets, debris from satellite collisions and anti-satellite weapon tests, and countless other fragments circle the planet at speeds exceeding 28,000 kilometers per hour in low Earth orbit. At these velocities, even a paint fleck carries enough kinetic energy to damage spacecraft, and larger debris can be catastrophic. Several satellites have been destroyed by collisions with debris. The collision of Iridium-33, an operational communications satellite, and Cosmos 2251, a defunct Russian military satellite, in 2009 created over 2,000 trackable pieces of debris larger than 10 centimeters and countless smaller fragments. The Chinese anti-satellite test in 2007, which deliberately destroyed one of their own defunct weather satellites, created over 3,500 trackable debris pieces in one of the most heavily used orbital zones. Each collision creates more debris in a cascade effect, and debris fragments colliding with each other create even more pieces. Currently, there are approximately 34,000 pieces of debris larger than 10 centimeters being tracked, about 900,000 pieces between 1 and 10 centimeters, estimated but too small to track individually, and over 130 million pieces smaller than 1 centimeter. Even millimeter-sized pieces can damage spacecraft, pitting windows and degrading solar panels. The Kessler syndrome is a nightmare scenario for space operations, a cascade of collisions creating exponentially increasing debris that could make certain orbital zones unusable for decades or longer. Proposed by NASA scientist Donald Kessler in 1978, the syndrome describes a threshold where debris density reaches a critical point such that collisions between debris objects generate new debris faster than atmospheric drag and other processes remove debris. Above this threshold, even if no new satellites were launched, collisions would continue to cascade, creating an exponentially growing debris population. Some researchers worry we're approaching this threshold in low Earth orbit, particularly in the heavily used region between 800 and 1,000 kilometers altitude, where atmospheric drag is too weak to remove debris quickly, but satellite density is high. If the Kessler syndrome begins in earnest, it could trap humanity on Earth by making spaceflight through certain orbital shells extremely hazardous, like traveling through a cloud of bullets moving at hypersonic speed in random directions. Cleaning up space debris has become an urgent priority.
Various solutions have been proposed, using lasers to nudge debris into atmospheric re-entry, nets or harpoons to capture large debris, magnetic systems to collect metallic fragments, robotic servicers to refuel and repair satellites to extend their lives, and international agreements to limit debris generation. But the technical and economic challenges are enormous, and international cooperation is essential since space debris doesn't respect national boundaries. Earth's shadow extends far into space, a cone of darkness pointing away from the sun. During a lunar eclipse, the moon passes through Earth's shadow, experiencing what would be from the lunar surface a total solar eclipse as Earth blocks the sun. The shadow has two parts, the umbra, where Earth completely blocks the sun's direct light, and the penumbra, where Earth blocks only part of the sun, creating partial shadow. The umbra extends about 1.4 million kilometers into space on average, though the exact distance varies as Earth's distance from the sun changes throughout the year. During a total lunar eclipse, the moon often appears red or copper-colored rather than going completely dark. This happens because Earth's atmosphere bends and scatters sunlight around the planet through refraction and Rayleigh scattering, the same process that makes sunsets red. All the sunrises and sunsets happening on Earth at that moment project onto the lunar surface, creating the blood moon appearance. The exact color varies based on atmospheric conditions. Volcanic eruptions that inject particles into the stratosphere can make the moon appear darker red or even nearly black during eclipses. The sun's light takes 8 minutes and 20 seconds to reach Earth, traveling at the universe's speed limit of about 300,000 kilometers per second. If the sun suddenly vanished, which is physically impossible but useful as a thought experiment, we wouldn't know for 8 minutes and 20 seconds. For that brief time, we'd still see sunlight, feel its warmth, and continue orbiting the now absent sun. Gravity also propagates at the speed of light, according to general relativity, so Earth would continue following its orbital path for those 8 minutes before flying off on a tangent into space. This illustrates an important property of the universe. Causality cannot propagate faster than light speed. We're always seeing the past when we look at distant objects. The Sun, as we see it, is 8.3 minutes in the past. Jupiter is between 35 and 52 minutes in the past, depending on relative positions. The nearest star, Proxima Centauri, is 4.24 years in the past. When we look at distant galaxies through telescopes, we're seeing them as they existed millions or billions of years ago. Some of those galaxies may have changed dramatically or even ceased to exist by now, but we won't know for millions or billions of years until light from those events reaches us. We inhabit a universe where information about distant events takes time to propagate, and we're surrounded by images of the past.
The sun's influence extends far beyond its light and warmth. The heliosphere, a vast bubble of solar wind, envelops our solar system, and protects it from the interstellar medium and galactic cosmic rays. The Sun constantly emits the solar wind, which inflates this bubble to enormous size. The heliosphere extends well beyond Pluto's orbit, with its boundary, the heliopause, located about 120 astronomical units, 18 billion kilometers, from the Sun. At the heliopause, the solar wind pressure balances the pressure of the interstellar medium, creating a boundary between solar-dominated space and interstellar space. Voyager 1 crossed this boundary in August 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018, crossing at a different location and providing insights into the heliosphere's structure. Both spacecraft detected sudden increases in cosmic ray flux and changes in plasma properties as they crossed the heliopause. The heliosphere shields the inner solar system from the full intensity of galactic cosmic rays, which are partially deflected by solar magnetic fields embedded in the solar wind. Without this protection, cosmic ray flux in Earth's vicinity would be higher, potentially affecting atmospheric chemistry, climate, and the evolution of life over geological timescales.
Every atom in your body heavier than hydrogen was forged in a star billions of years ago. You are literally made of stardust, a poetic fact that also happens to be scientifically true. Hydrogen formed in the Big Bang, but all heavier elements were created through stellar nucleosynthesis. Inside stars, nuclear fusion creates progressively heavier elements. Hydrogen fuses into helium, helium into carbon and oxygen, and in massive stars, the process continues through neon, magnesium, silicon, and eventually iron. But iron is the end of the line for fusion. Fusing iron consumes energy rather than releasing it, so fusion stops. Elements heavier than iron are primarily created in supernova explosions when massive stars die.
The intense heat and neutron flux during supernovae create elements like gold, platinum, uranium, and all the other heavy elements through rapid neutron capture. When stars die, either gradually as planetary nebulae for stars like the Sun, or explosively as supernovae for more massive stars, they scatter these elements across space. Eventually, this enriched gas coalesces into new stars and planets. The Sun and Earth formed from gas enriched by previous generations of stars. The carbon in your cells, nitrogen in your DNA, calcium in your bones, iron in your blood, oxygen you breathe, all were created in dying stars billions of years ago.
Some elements, particularly gold, platinum, and other heavy elements, require even more extreme conditions than typical supernovae. Recent research suggests that collisions between neutron stars, some of the most violent events in the universe, are the primary source of the heaviest elements. In 2017, astronomers observed a neutron star collision through both gravitational waves and electromagnetic radiation, confirming that these collisions produce heavy elements. You are assembled from atoms with cosmic biographies spanning billions of years and multiple stellar generations.
Earth's location in the Milky Way galaxy is unusually safe, perhaps necessarily so for complex life to evolve. We orbit in what astronomers call the galactic habitable zone, roughly 26,000 light-years from the galactic center in a relatively quiet region between spiral arms. This location matters. Closer to the galactic center, stellar density is much higher, increasing the probability of close stellar encounters that could disrupt planetary orbits. Supernova frequency is higher in regions of active star formation, and frequent nearby supernovae would bathe planets in sterilizing radiation. The supermassive black hole at the galactic center and the intense radiation environment around it would be inhospitable.
Conversely, in the galactic outskirts, far from the center, there wouldn't be enough heavy elements, metals in astronomical terms, meaning anything heavier than hydrogen and helium, to form rocky planets or the complex molecules life requires. The Sun orbits in a relatively stable region with enough heavy elements for planet formation, but far enough from hazards like supernova to allow life billions of years of relatively undisturbed evolution. Additionally, we're currently passing through a region of lower interstellar dust density, called the local bubble, created by ancient supernova that swept the region clear. This reduces the flux of cosmic rays somewhat.
Of course, we can't know if this location is necessary for life. We only have one example. But it's plausible that galactic location influences habitability over the long timescales required for complex life to evolve. Our solar system is traveling through space at approximately 828,000 kilometers per hour, 230 kilometers per second, relative to the cosmic microwave background, the faint afterglow of the Big Bang that serves as a cosmic reference frame. But motion is relative and hierarchical at multiple scales. Earth orbits the Sun at about 107,000 kilometers per hour, completing one orbit per year. The Sun orbits the galactic center at about 828,000 kilometers per hour, taking roughly 230 million years to complete one orbit, one galactic year or cosmic year. The Milky Way galaxy itself moves through space within the local group, a collection of about 54 galaxies, dominated by the Milky Way and the Andromeda galaxy. The local group, in turn, is falling toward the Virgo supercluster, a massive collection of galaxies about 65 million light-years away. The Virgo supercluster is itself part of an even larger structure called Laniakea, which includes about 100,000 galaxies and is being pulled toward a region of space called the Great Attractor. At every scale, planetary, stellar, galactic, and cosmic, we are in motion. The ground beneath your feet is hurtling through space at hundreds of thousands of kilometers per hour, but so is everything around you, creating the illusion of stillness. We are never still. We live in a universe of constant motion.
And yet, from space, Earth looks fragile, a perspective that has profoundly affected many astronauts who have seen it. They describe the overview effect, a cognitive shift in awareness when seeing our planet as a small, delicate sphere floating in the void. From the Moon or from distant space, Earth appears as a tiny blue and white marble suspended in infinite blackness, with no visible borders, no divisions, no signs of the conflicts that dominate our news. The atmosphere, which seems vast and unlimited from the surface, appears as a thin blue line, barely there, fragile as tissue paper.
Astronauts consistently describe the experience as deeply emotional and transformative, changing how they think about humanity, borders, and our place in the universe. Edgar Mitchell, Apollo 14 astronaut, described it as a glimpse of divinity. Seeing Earth from space emphasizes its isolation. There's nothing nearby, just void in all directions for unimaginable distances. It emphasizes its beauty, swirling clouds, blue oceans, brown and green continents. And it emphasizes its fragility. That thin atmosphere is all that separates life from the void, and the planet itself, while large to us, is a mote of dust on a cosmic scale. This perspective has inspired environmental awareness and space advocacy, reminding us that Earth is the only home we have, at least for now, and its protection matters in ways that transcend national boundaries and short-term interests. So here we are, having journeyed together through 100 facts about Earth, each one a window into the extraordinary nature of our home planet. We've seen that Earth is not a static rock, but a dynamic, living system. Continents drift on an ocean of molten rock, moving with the patient inevitability of geological time. Mountains breathe with the seasons, growing and shrinking as rock expands and contracts. The ground beneath our feet hums with vibrations too deep to hear, the planet singing its endless note. Hidden oceans exist within the mantle, holding perhaps more water than all surface seas combined. The magnetic field that protects us flips periodically, north becoming south, and may be preparing to flip again. The moon drifts slowly away, lengthening our days millisecond by millisecond across the eons. We've descended into oceans that glow with bioluminescent life, hide underwater waterfalls larger than any on land, and host ecosystems thriving near boiling volcanic vents without sunlight. We've discovered that the ocean sings with whale songs traveling thousands of kilometers, that coral reefs synchronize spawning across hundreds of miles, that deep trenches harbor life under pressures that should crush all living things. The ocean absorbs our carbon emissions, slowing climate change, but acidifying in the process, threatening the foundation of marine food webs. We've marveled at life that defies our assumptions about what's possible. Immortal jellyfish that reverse aging, tardigrades that survive space, extreme heat and cold, and radiation that would kill any other known organism. Bacteria sealed in salt for 250 million years that can be revived. Vast ecosystems kilometers beneath the surface, divorced from sunlight, where bacteria divide perhaps once per millennium. Organisms thriving in volcanic heat, in acid, in radioactive waste, in every extreme environment Earth offers. Plants that communicate through fungal networks and airborne chemicals. Trees older than civilization. Animals that survive being frozen solid and then revive as if nothing happened.
We've witnessed landscapes that move and remember, stones that walk across desert floors under the right conditions, fairy circles forming geometric patterns across grasslands, forests migrating slowly poleward as climate warms, deserts that bloom once a decade when rain finally comes, ancient aquifers holding water that fell as rain when the Sahara was green, rivers that disappear into desert, never reaching the sea, underground cave systems larger than buildings with their own weather, rocks that remember magnetic fields from billions of years ago, preserving Earth's history in their atomic structure.
And we've explored Earth's connections to the cosmos, the constant rain of cosmic dust adding tons of material daily, auroras painting the sky when solar wind collides with our magnetic field, cosmic rays from distant supernovae showering through the atmosphere, occasionally flipping bits in computer memory, the protective magnetosphere extending over 1 million kilometers into space, asteroids that have repeatedly reshaped life on Earth, opening opportunities even as they brought destruction. The fact that we're made of elements forged in dying stars, that we are the universe becoming conscious of itself, matter examining its own nature. Earth is not ordinary. It never was. It is ancient, 4.54 billion years old, yet constantly renewing itself through plate tectonics and the recycling of rock, water, and even atmosphere. It is stable enough for life to persist for billions of years, yet dynamic enough to constantly create new environments and evolutionary opportunities. It is familiar. We know its mountains, oceans, and skies, yet alien when we examine it closely, filled with phenomena that seem impossible, yet undeniably exist. We live on a world where mountains grow and breathe, where forests communicate underground, where oceans glow in the dark and sing songs that cross thousands of miles, where life persists in the most impossible places and adapts to conditions that should be instantly fatal, where stones walk, rivers run backward, and deserts bloom once in a lifetime, where rocks remember magnetic fields from eons past, and crystals grow for 500,000 years, where the ground itself moves, carrying continents across the globe over the ages.
And we live on a fragile world. For all its age and size, for all its power and resilience, Earth exists in a delicate balance. The magnetic field could weaken or reverse, exposing life to increased cosmic radiation. Ocean currents could shift, dramatically altering global climate patterns. The thin atmosphere that sustains us leaks slowly into space, and without volcanic replenishment would eventually vanish. The biodiversity that makes ecosystems resilient, the countless species working together in ways we're only beginning to understand, is disappearing at rates not seen since the asteroid that killed the dinosaurs.
Every discovery we make about Earth reveals how improbable this place is. How many specific conditions must align for a planet to remain habitable for billions of years? The right distance from a stable star, the habitable zone where water can exist as liquid, a large moon to stabilize the axial tilt, preventing wild climate swings, a molten iron core generating a protective magnetic field, plate tectonics recycling minerals and regulating atmospheric carbon dioxide over geological time,
a location in the galaxy safe from sterilizing radiation but rich enough in heavy elements to form rocky planets.
Jupiter's gravity deflecting many asteroids that might otherwise strike Earth. All these factors and more combine to make Earth not just habitable, but a cradle for complex, intelligent life. We are one species among millions on this planet, each one a solution to the problem of survival, each one interconnected in networks we're only beginning to map. We are made of atoms forged in dying stars, arranged by chance and evolution into beings capable of understanding our own origins. We stand on ground that moves imperceptibly but inexorably through space at hundreds of thousands of kilometers per hour. We breathe air that glows with auroras at the poles. We drink water that has cycled through this planet for billions of years, passing through countless organisms before reaching us.
So take a moment, right now. Look around. Feel the ground beneath you. Ground built from rock billions of years old. Ground that tells stories written in minerals and fossils. Ground that is traveling through space faster than you can imagine. Listen to the wind. Air molecules that have been breathed by countless organisms before you. Perhaps by dinosaurs, ancient humans, trees that lived centuries ago. Look at the sky. Those photons left the sun 8 minutes ago, traveling through the void at the speed of light to reach your eyes at this exact moment.
Remember that you are standing on a planet that is far stranger, far more alive, and far more connected than you ever imagined. A planet where the impossible is commonplace and the familiar contains hidden depths. A planet where geology and biology intertwine, where ocean and atmosphere exchange matter and energy, where life and rock shape each other over deep time.
Earth is the only world we know of certain harbors life. The only world where conditions aligned perfectly for billions of years to allow life to emerge, evolve, and eventually become conscious of itself. The only world where matter has organized itself to the point where it can contemplate the universe that gave it birth. And we get to call it home.
Thank you for joining us on this journey through the strangest facts about our home planet. If you found wonder in these discoveries, if you see Earth differently now, if you appreciate its complexity and fragility more deeply, then we've succeeded in what we set out to do.
Consider subscribing to Infinite Science. We explore the mysteries of the universe, one discovery at a time, with curiosity and awe as our guides, seeking to understand the cosmos and our place within it. Until next time, stay curious. Keep looking up and down and all around. Keep asking questions. Keep seeking answers. The universe is full of wonders, and Earth, this pale blue dot suspended in a sunbeam, this mote of dust floating in cosmic darkness, this improbable oasis of life in an apparently lifeless universe, is the greatest wonder we know. Stay curious and remember how extraordinary it is to exist on this strange and beautiful world.